Good afternoon, ladies and gentlemen. Thank you very much for taking time out of your busy schedules today to come to the annual symposium on the ITER project and BA activities, fusion energy that creates a new future. My name is Yoshima Fukui of the QST, Kazuma Fukui of the QST, and I will be moderating today's symposium. I am usually engaged in research and development of superconducting coils for the tokamak-type fusion experimental device JT60SA at the Naka Fusion Institute of QST. Thank you very much for your cooperation in advance. First, on behalf of the organizers, I'd like to ask Mr. Sawa Takumitsu, chairperson of the Fusion Energy Forum of Japan, to say a few words. As chairperson of the steering committee of the Fusion Energy Forum of Japan, allow me to express my sincere gratitude to many participants from different disciplines for sparing time out of your very busy schedules to be here. The Fusion Energy Forum of Japan, the hosting organization of this meeting, was established to support R&D toward the realization of fusion energy and is made up of a large number of voluntary participants, in addition to experts from different fields who agree with its purpose. Today, as in the case of last year, we limited the number of seats in this hall in consideration of the COVID. To compensate for that, the entire session will be simultaneously live-streamed via YouTube in both English and Japanese in a so-called hybrid conference format. On October 26, 2020, former Prime Minister Suga declared carbon neutrality by 2050 in his policy speech at the beginning of the extraordinary session of the Diet. What he meant by this was to achieve virtually zero emissions of greenhouse gases, including CO2, by 2050. Ever since, decarbonization has become one of the most important keywords when discussing energy and environmental issues. The key to decarbonization is to reduce the share of fossil fuel power sources as much as possible and to promote the electrification of homes and businesses, including EVs. As to the power sources, public opinion is sharply divided on whether to rely on nuclear power or renewable energy for decarbonization. Public opinion is also divided on whether we should seek for large-scale centralized system or small-scale decentralized power generation system. Unfortunately, fusion energy has yet to emerge as an option in this kind of a debate. It has been said now and also in the past that fusion energy will become one of the decarbonized power sources in 30 years. Why is it always 3 decades down the road? The reason is quite simple. There has never been a real need for fusion energy, at least until now. In order for fusion energy to be truly needed in the not-so-distant future, at least 2 things are necessary. One is the certainty that there will be a rapid increase in the power demand. This should be confirmed. The The second is that the cost of producing hydrogen from fusion power or from small fusion reactors is expected to be sufficiently low. Then, what will be the transition of the power demand in the next 10 to 20 years? Declining population, power-saving electrical appliances, and reduction on the people's mobility will certainly reduce power demand. On the other hand, as autonomous driving becomes more widespread and AI is put to practical use in many ways, data centers that consume large amount of power will become indispensable. This is because safe driving will be achieved by exchanging data between the vehicle and the data center, rather than by installing advanced computers in each vehicle. According to a calculation, each fully automated car uses as much power as a standard household. There are many uncertainties, such as how much the widespread use of AI will increase the demand for electricity, how widespread the autonomous driving will be, and whether it will be possible to have data centers overseas in countries with low power prices such as Canada, Iceland, and Norway. What is required here is a detailed analysis and forecast of what will happen to domestic demand for electricity. The cost of the nuclear fusion power generation and hydrogen production will be prohibitive, at least for the time being. However, once the fusion technology is close to perfection, the focus of technological development will be on cost reduction, and I hope that young researchers will work on reducing the cost of power generation by fusion to a level comparable to that of light water reactors and renewables. The same can be said with the cost of hydrogen production. I'd like to conclude by wishing for the future promotion of cutting-edge nuclear fusion research, and especially for the development of young researchers who will be the bearer of such research. Thank you very much.
Thank you indeed, Mr. Sawa, Chairperson. Now, despite the busy schedule, we are honored to have the guest of honor. First, from the LDP, we have Mr. S.K. Mori, the chairperson, the League of DAT members of the Fusion Energy Promotion. Without further ado, Mr. Mori, please. Good afternoon, ladies and gentlemen. Thank you again for the kind introduction. This is S.K. Mori, chairperson, the League of the DAT members and for the Fusion Energy Promotion, the Liberal Democratic Party of Japan. It is a great honor to participate this year again in this annual symposium on the ITER project and the BN activities, which brings together all the parties concerned. This gives me the personal pleasure and an honor. Fusion is becoming increasingly important in today's world, and from the perspectives of carbon neutrality and energy security. The growing importance of pulsing for the fusion energy has led major countries to promote government-led initiatives and to expand investment into fusion the ventures. And now we are entering an era of international competition. Under these circumstances, we, the LDP, are actively promoting policies to promote fusion energy R&D activities under the leadership of Prime Minister Kishida, who was elected in the presidential election on the platform of formulating a national strategy for nuclear fusion. That said, and I believe the most important project to realize fusion energy is the ITER project and the BA activities being held today. Japan has been leading this project since day one, and do allow me here to offer my sincere respect to all the people involved in these very important initiatives. The ITER project is a symbolic international project driven by the 35 countries in the 7 major regions of the world. Do allow me first here to offer my sincere condolences to the late Bernard Bigot, the former Director General of ITER, who passed away in May this year. Since then, under the leadership of Dr. Eisuke Tada, who served as the interim Director General, the ITER construction is progressing steadily and firmly. I am fully aware that now, under the leadership of the new DG, Pietro Barbaschi, being supported by the many Japanese stakeholders, the project is well underway. So allow me here to express my sincere appreciation going to every one of the people concerned. The BN activities hosted by Japan are progressing smoothly in Rokashi Village in Aomori and Naka City, Ibaraki, driven by the international cooperation between Japan and Europe, and with the energetic support of the local communities. The JT60 SA at Naka site is about to start the integration and conditioning operation, but we recognize that the road to success has not been a smooth one, and that it is the result of the overcoming many difficulties and with the passion of everyone involved. I do hope that many of the findings and insights obtained from these experiences will be applied to the ITER project as well as to the prototype reactor, which will drive the ITER project success and making contributions to the realizing the fusion power generation at an early stage. QST and many other heavy electric machinery companies are making their best efforts in order to realize this demo of the expectation. The collaboration among the industry and the government and in academia will become more critical. So here I would like to beg you to try to have more keen interest in this fusion energy. I strongly believe that in all the people concerned be united, the ITER project and the BA activities will surely succeed. We LDP, the League of the Diet members for the fusion energy promotion, will collaborate with the government and the promise here to firmly support your activities. Last but not least, by expressing my sincere appreciation for your effort and contributions by Dr. Takamitsu Nasawa and all the other members of Fusion Energy Forum of Japan. With this, I'd like to conclude my remarks. Thank you indeed.
Thank you, Mr. Mori. We would like to ask for remarks from the Deputy Minister for Education, Culture, Sports, Science and Technology, Mr. Masuko Hiroshi. Good afternoon, and thank you for the introduction. I'm Masuko, Deputy Minister for Education, Culture, Sports, Science and Technology. I'd like to deliver my remarks on the occasion of the ITER BA 2022 Symposium. I'm pleased to see so many people who are involved in or interested in ITER and BA activities and nuclear fusion. I'd like to take this opportunity to express my sincere appreciation for the efforts that you are making every day. Globally, the Ukraine crisis causing soaring energy prices, and other factors have led to heightened awareness about energy security and carbon neutrality. Fusion energy is expected to contribute to the realization of these goals, and international competition is accelerating as major countries are formulating national strategies and venture companies are being formed. In Japan, under the leadership of Prime Minister Kishida, various measures are being actively implemented to realize fusion energy. In September of this year, under the Cabinet Office's Council for Integrated Innovation Strategy, an expert committee on fusion strategy was established where they are discussing toward the formulation of a national strategy for fusion. The ITER project and BA activities, which are the subjects of today's symposium, are very important initiatives that will serve as the two wings of a bird for the early realization of fusion energy. In the ITER project, equipment manufactured by each of the parties, including superconducting coils made in Japan, have been delivered, and their assembly is currently underway. We expect that this project will be steadily promoted under the leadership of the new Director General, Dr. Pietro Barbaraschi, of the ITER organization. BA activities are now in their 16th year since the agreement entered into force, and the 3rd year since the start of Phase 2. The world's largest fusion experimental device, JT60SA, is moving toward start of experimental operation in Naka City, Ibaraki Prefecture, and an international fusion research and development center is being formed in Rokkasho village of Aomori Prefecture. So various operations are steadily moving forward. At our ministry, next, we will continue to vigorously promote R&D and human resource development for fusion energy, including ITER, toward the realization of fusion energy. Now, there is an extremely long path to travel before we can put fusion energy to practical use. To succeed in this dream project that will create a bright future, it is essential to develop and secure excellent human resources to support the project. I'm sure that students and young researchers and engineers are participating today. I ask you to continue to participate in this project so that we may create a bright future together. I ask for your sincere cooperation. In conclusion, I'd like to express my sincere gratitude and respect to Dr. Sawa Takamitsu and the Fusion Energy Forum of Japan, Mr. Mori Eisuke, Chair of the League of Diet Members for Fusion Energy Promotion of the LDP, members of the Diet, people from industry and academia, and all of you who are here today. Thank you very much for your participation.
Thank you very much, Mr. Masuko. Next, we'd like to invite Mr. Izumisawa Seiji, Chair, Committee on Mutsu Ogawara Development, Japan Business Federation, President and CEO, Mitsubishi Heavy Industries. Thank you very much for your introduction. I am Izumisawa, Chairman of the Committee on Mutsu Ogawara Development of Keidanren, and I am also CEO of Mitsubishi Heavy Industries. I am in charge of promoting the development of the Mutsu Ogawara Development Area, where QST's Rokkasho Research Institute is located. I'd like to say a few words from the viewpoint of the business community. Congratulations for this year's ITER BA annual meeting. The importance of energy security and stable energy supply has been reaffirmed internationally amidst the growing uncertainty over resource procurement due to Russia's invasion of Ukraine. Against this backdrop, green transformation, or GX, a transformation of the entire economy and society, is indispensable to achieve a stable and affordable energy supply while aiming for carbon neutrality at the same time. Under the leadership of Chairman Tokura, Keidanren compiled a proposal for green transformation this past May. Meanwhile, as has been mentioned earlier, the government established the GX Execution Council at the Prime Minister's office in July. At its second meeting in August, the Prime Minister instructed the Council to accelerate the re-examination of energy policy, including nuclear power, and the relevant advisory councils are now discussing the issue. In the discussions, they are also considering the continuous use of nuclear power generation and the development of the construction of next-generation innovative reactors. The business community is looking forward to a clear direction from the government toward the active use of nuclear power, which is a decarbonized energy source that is not affected by energy market conditions. Among the next-generation innovative technologies, nuclear fusion energy is relatively safe in that it can be easily shut down by stopping the supply of fuel, and there is no risk of depletion of fuel resources. Fusion energy does not generate high-level radioactive waste, which is also a major benefit. We believe that the commercialization of fusion power generation will make a significant contribution to Japan's energy problems and to addressing global climate change. We hear that ITER, an international fusion project, is making steady progress with almost 80% of its construction completed, thanks to the efforts of everyone concerned. We look forward to the realization of first plasma in 2025 and full-scale operation in 2035 of ITER, and we are more than ready to provide any support that is possible. As for BA activities, I understand that relevant researches are progressing toward the establishment of the technological basis required for the fusion demo reactor, and that the Rokkasho Research Institute, Naka Fusion Institute, and other facilities related to BA activities have become centers of development for young researchers from all over the world. We believe it is extremely important for the government to provide further support to create an environment where the young researchers can work with dreams and hopes. And we are receiving the tremendous support from the community. I have also heard that technologies derived from fusion R&D, such as lithium recovery and low-temperature ore refining technology, have recently emerged. Fostering these technologies into viable industries is also important. Looking around the world, in parallel with ITER and the BA, each country is independently accelerating large-scale efforts toward the realization of fusion power generation. It is imperative for Japan to also promote development of fusion power generation as a national strategy. The Cabinet Office's expert committee on fusion strategy has started to discuss the formation of the strategy in September. We hope that the clear strategy, including the development of technology and securing human resources, and the mobilization of funds will be presented to maintain and strengthen the international competitiveness of Japan's technology, which will lead to the practical application of nuclear fusion. Finally, I'd like to offer my deepest condolences to the passing of Dr. Bernard Bigot, the Director General of ITER. I echo the condolences presented by Dr. Mori. Dr. Bigot visited our plant in Kobe in January 2020 for the completion ceremony of the first toroidal coil and kindly gave us a congratulatory speech. When I asked him about the essential requirements of managing a big project like ITER, in which many countries participate, he replied that professionalism, trust, transparency, team, common rules, and commitments are all important. I hope that Dr. Bigo's legacy will be handed down, and under the leadership of the new Director General, Dr. Barak-Belsky, the next generation of researchers and engineers will continue to promote the ITER project. I'd like to conclude by wishing that today's symposium will be an opportunity for further progress in fusion research and development. Thank you.
Thank you, Mr. Izumisawa. Next, from Keizai Doyukai, or Japan Association of Corporate Executives, we have the Executive Director and also Chair of the Environment and Energy Committee, Ms. Mitsue Kurihara. She's also Chairperson of the Value Management Institute. Greetings to you all, and thank you for the introduction. I am Kurihara, Vice President of Keizai Doyukai and Chair of the Environment and Energy Committee. It is a great honor for me to attend and address the Fusion Energy Forum ITER BA Annual Symposium 2022. Now, I believe that many of you here today are involved in fusion technology and or related industries. However, for those of us like myself who have been in the financial world for a long time, although we have been involved indirectly through the financial sector, until recently, we thought that this technology was still a dream for the distant future. And regrettably, I believe that many people in management in the corporate sector still think that way. However, I have now come to understand that the era of saying that this is a dream technology for the distant future is over. It is a dream technology for sure, but I now recognize that the time has come for international competition and strategic coordination towards its implementation. I am sure that we can hear updates about various results today, but I have been informed that the ITER project, which we, the Keizai Doyukai, visited in 2019, 3 years ago now, has progressed to 77% construction of the experimental reactor and will start operation around 2025. The development of JT60SA, fusion neutron source, a blanket, and other BA activities are also progressing. If these various technological developments are integrated into the development of the next demo reactor, we expect to be able to complete a fusion plant with a competitive advantage in Japan. Now, concerning this demo plant, the UK, the US, and other countries have already formulated strategies for the construction and operation in the 2030s and 2040s, and international competition is intensifying. I hope that Japan will position fusion energy development as a clean energy for the future, as a domestic energy that is important for economic security, and as a field where Japan can make an international contribution and will strategically promote its implementation in society. Now, this technology, it can be applied not just to energy, but also to a wide range of fields such as medicine, space, and transportation. and it is expected to lead to the advancement of industry and the creation of new markets. As a member of industry, I believe it is important to widely share the results of these various developments and their potential for development, and increase the predictability of their realization through a long-term roadmap, and then to develop an industry around the technology. Furthermore, it is necessary to form new supply chains and industrial clusters. It is important that a variety of actors, including companies that already have technology, market, and human resources, and venture companies, universities, and research institutes collaborate as implementing parties. And human resources is most important. We need a system and culture in which experienced and young people can work together to share their wisdom and increase the amount of challenges that they take on. We in the business community would like to take up the challenge and collaborate to play a role in the creation of new value. I hope that today's symposium will help to develop cooperation between R&D and industry and across industries. I also hope that the organizer, Fusion Energy Forum of Japan, will connect various participants and further expand the number of participants and further develop as a platform for promoting development toward the realization of fusion energy. Thank you so much.
Thank you indeed, Ms. Kurihara. We have just received the excellent remarks, but also now we have many guests. Let me introduce them. Again, the introductions will be made in order from left to right and from the audience to the stage. Yoshiaki Wada, member of the House of Representatives, the Vice Minister of the Cabinet Office. Thank you. Mr. Masaaki Akaike, a member of the House of Councillors. Thank you. Mr. Yuichiro Wada, member of the House of Representatives. Thank you indeed. Mr. Shuji Kira, member of the House of Representatives. Thank you. Mr. Yasushi Katsume, member of the House of Representatives, and actually his secretary is here instead. Rokkasho Nomura, and actually the mayor, Mr. Mamoru Toda. Thank you. Also, we are honored to have received many the congratulatory remarks in the form of the telegrams, and due to time factor, I'm going to introduce just some of them. Actually, Vice Minister, the Asako Omi, Ms. Ami, also from the representative of the representatives, and Yaoso Amato, and also the member of the House of Councillors, Kuniko Niguchi, and also Shinji Moriguchi, from the member of the House of Councillors. Thank you indeed for your remarks. Now we'd like to move into the keynote presentation.
First, we will hear about the status of ITER construction. We have received a video message from Dr. Pietro Balabaski, Director General of ITER organization, who took office in September this year. Then Dr. Eisuke Tada, Deputy Director General of ITER organization, will give us his report. Now we play the video message from Director Borobaski. Please watch.
Konnichiwa. Ohisashiburi desu. Greetings from the Fusion Energy Forum from the ITER site here in Provence. It is a real pity for me not to be there with you. I would have really liked to be with my colleagues and Japanese friends. I know that I would see many familiar faces. As you know, I worked in my previous role as Fusion for Energy Coordinator in the broader approach activities. So, yes, as many of you know, the BA has been my second family in my last 15 years. And before then, yes, I was working also again in the ITER project where I worked with so many of you. Indeed, I'm pleased to learn that this annual forum is the place where both ITER and BA in Japan will be jointly reported. And so I am very much delighted that I could contribute in my professional life to both of them, and I could interact with many of you. I deeply respect my Japanese colleagues from QST and other institutions in Japan. So since 2007, as many of you know, I've worked in this European-Japanese collaboration of fusion development, where I was in charge of the European contributions, where I interacted with my Japanese friends and brothers in arms, so to say. We work very closely as a single team, and I think we have demonstrated together how we could collaborate effectively. And I really hope that this experience will be instrumental, carrying this experience will be instrumental in improving the way we collaborate also in the ITER project. Now, for the first time, I am talking to you in my new role as Director General of the ITER project. It is for me a great honor to have been asked to take on this job, to some extent unexpected. But okay, I am taking this with all my heart and all my commitment. It is also important for me, essential, I would say, to pay tribute to my predecessors. Dr. Ikeda and Professor Motojima, and of course also Bernard Bigot, that unfortunately recently passed away. I want also to pay tribute to my colleague, my friend, Tada-san, who is there with you, and that will represent the ITER project at your conference. He's teaching me many things, and I'm very grateful for what he has done during this difficult interim period that he had to take on, and also all the help that he's providing me in this learning phase. Together with my Japanese friends, we have worked well, and we have developed the so-called BA way to work together. And I think we shall be able to build a new way to work together, say the ITER way to work together, that will mimic, to a large extent, what we have done together in the BA. So, yes, I can tell you from by bottom of my heart and my observation that from the very early days of the ITER project, Japan has played a very important pivotal role, not only in leadership, but also in design and manufacturing, in fusion research. And the friendship that we developed between Europe and Japan has been so important to develop jointly together these wonderful projects. Japanese engineering is present throughout the ITER tokamak and its support system, the toroidal field magnet, the superconducting material of the central solenoid, the neutral beam test facility, the blanket remote handling, the divertor, the electron cyclotron launcher, and so many other things. Perhaps more importantly, I have consistently witnessed the rich expertise of Japanese scientists and engineers contributing to the fusion research and development program. Now that we are at the assembly and installation phase, these in-kind contributions from Japan, together with similar contributions from all the other 6 ITER members, they are beginning to take place as a single experimental device. Naturally, this is where the project becomes even more challenging, where some of the issues come afloat, and this is where we must ensure quality at the highest level, both in the components and also in the project culture. It is also vital for us to ensure a strong relationship with the French safety regulator, which is in some sense one of our stakeholders. We know we will have some setbacks. Yes, this is normal for such a complex device and first-of-a-kind project, but I am convinced, I can say, based on my experience, especially thanks to my experience in the BA with my Japanese colleagues, I am confident that we will overcome these challenges and continue working together forward as long as we work as a single ITER team. I am very pleased that in my new role as ITER DG, I will continue to have the pleasure to interact with many long-term Japanese friends and colleagues whom I deeply respect, and I wish you every success in this forum, and I hope to see you all soon, either in Japan on the ITER site, and hopefully next time you will all meet again in the forum. Thank you.
Next, we have Dr. Tada Eisuke, Deputy Director General of the ITER organization, to make a report. Please. Thank you for the introduction. I'm Tada with the ITER organization. Thank you very much for this opportunity to report on the progress of the ITER project at the Fusion Energy Forum Annual Symposium. With your support and cooperation, the ITER project is making steady progress. Once again, I'd like to thank you so much for your support. Following the message from the Director General, I would like to report on the status of ITER construction. First, regarding the progress of the ITER project as a whole, although there have been some delays due to COVID and other factors, but as you can see in this photo, work at the construction site has been progressing steadily. Specifically, in terms of civil work, about 85% has been completed so far, and 78% of the work required for the first plasma has been completed. This is a general view of the ITER construction site taken in May 2020. Except for the control building or control room and the neutral beam power supply building in the foreground, except for those two, all other buildings and facilities have been completed. Installation of plant facilities has progressed since then, and the installation of the power supply system and the cooling cryo plant system is almost completed and entering commissioning as they are readied. Moreover, assembly of tokamak equipment is progressing at the tokamak building and the assembly building after they have been transported to those locations. So this photo taken in October this year shows how the site looks. Lower left is the control building, and its construction is almost completed. And so equipment is being installed. Tritium building, and then helium, well, the bridge to support cryo lines between cryo plant and tokamak building on the lower right, they are also progressing. And so installation of the equipment has begun. So in parallel with the installation, commissioning of plant facilities is also in progress. This photo shows the helium refrigeration system, and that is almost completed, and we're now entering commissioning. This helium refrigeration system is capable of producing 16,000 liters of liquid helium per hour. It's the biggest in the world. And commissioning of the liquid nitrogen facility has been completed, and commissioning of the helium compressor on the left is currently being undertaken. As soon as that is completed, we go to the right. The cold box, the helium refrigeration system itself will start to be commissioned. So this shows the appearance of the entire cooling system, and last August, installation has been completed and commissioning has started. Motors, pumps, and other main components, commissioning has already been completed. We're doing Kodak and measurement control system combination tests. And then you see on the left cooling tower. And so we will do start commissioning of the cooling tower. So this is the coil power system. Left-hand side is AC-DC converters. Right-hand side is bus bars. You see installation situation almost all completed, and now commissioning is being started sequentially. And finally, the helium circulation system to maintain superconducting coils and other components, cryogenic, have been installed. As you see on the left, installation of the complex cryoline and the helium refrigeration system being connected to the tokamak, the so-called bridge piping. They are in progress. And so 75% of the installation of the complex cryoline piping has already been completed, and commissioning is starting in due course. And the fabrication of the tokamak components is also making steady progress. As you know, ITER has a framework in which the participating parties share in the fabrication and delivery of components, and Japan is responsible for the fabrication of advanced components such as superconducting coils, heating devices, diverters, measurement systems, blanket remote maintenance equipment, and tritium removal systems. For the toroidal field coil, or TF coil, that Japan is responsible for, 7 out of 9 coils have already been fabricated and tested. Left-hand photo was taken in September this year when the 7th coil, TF number 15, was being transported to the ITER site. As for the NB heating system, full-scale performance tests are underway, as you see on the right, in Padua, Italy. And based on the results, we plan to manufacture and install the actual equipment.
As for the ECN heating system, we have completed the fabrication of 8 gyro trons, and we are responsible for. And actually, those 8 units have been already completed in terms of fabrication. And also, the diverter, actually, the prototype on the fabrication has been completed, as shown on the right-hand side. And using this prototype, and then final the performance test is going to be carried out before we move into the fabrications of the real unit. Moving on, as for the plasma vessel, of course, Korea is responsible for this. Actually, the 3 units has been produced in Korea, and actually, they have been already delivered to the local site. Left shows the 3rd the vacuum vessel, just arriving in the local site. So using this, now the assembly and actual operation is underway in tokamak. And toroidal, the field, the first coil, TF1 coil, actually this was made and tested in Russia. Actually, as of the last week, it has left Russia coming onto the local site. So by the end of this year, actually, they are supposed to be reaching the local site. Next are the PF1. Actually, these fields other than the coils, actually, they are actually made and also tested in the local communities. Actually, a total of the units out of 6 and 4 units have been already completed in terms of fabrication and testing. All in all, the natural current, natural helium, actually, coolant are now going to be provided through the heater. As for this heater, actually, this is actually being manufactured and actually tested in a very smooth way, as shown in the left-hand side. These units actually have been shipped to the construction site. Moving on, superconducting actually the cryostat. Cryostat actually in 30 meters in diameter and actually in 50 meters in height. And they are actually being installed and in local site. Actually, all the fabrication has been assembly has been completed. The left picture shows the really last phase and the top lid and actually has been actually completed, attached. This was taken in March 2022 this year. And actually, assembly and operations have begun on the central solenoid. Actually, 2 units have been already reached the site, as shown on the right-hand side. So using these the units, actually, the preparation for the assembly is well underway. Moving on, what you see here is that, well, actually, all these major, actually, the devices have been already delivered to the local sites. Actually, 14 total the field coils, 4 the PF coils, and 3 vacuum vessel sectors, 3, and 2 central solenoid the modules, CS. So now they are already delivered to the site. So using these units, and actually, we started working on assembly at Tokamak. This has been already introduced to you in the past. Actually, the cryostat tape, the base, has been installed into the tokamak, and this shows the operation of that and activities. Actually, it was taken. It was completed in May 2020. So as you see in the picture, actually 1,250 tons, the total the weight, quite heavy, but we succeeded. And based upon the cryostat, the device, then after that, cryostat and the lower cylinder, and also the thermal shield, and also in the bottom, we are going to have the poloidal or the coil number 6 coil, number 5 coil, and we have the first bottom correction coil. So we need to work on the assemblies of these units, and actually, by the end of 2021, actually, we were able to complete all these the expected workload. Moving into 2022. Actually, the vacuum vessel and the 2 toroidal fields actually coming from Japan are shown in here. And also, they used the sub-assembly using the heat-sealed sector module. This sub-assembly has been completed. As shown in here, actually, we use this the sealing crane for the final assembly, and this sector module actually weighs 1,250 tons. Actually, 9 pre-assemblies are now required to close the torus, and high accuracy is actually being required. After the assembly of the sector module, actually, issues were identified in the thermal shield and panels and cooling pipes. We discovered some leakage, and actually, this result into the stress corrosion cracking. So we are able to actually identify the cause behind this issue. So we are still working on these challenges, but because of the tokamak and assembly, actually, the work has been suspended, as shown in the left-hand side. The stress and corrosion identified in the cooling pipes, and actually, we decided to work on the specific procedures and for the repair work and also on the testing. So we are going through these details right now. And looking at we would like to actually avoid the delay as much as possible. For example, actually in the vacuum vessel, the sectors are shown on the right-hand side. So actually, heat sealed and the repair. Actually, this work is going to be done in the parallel, and also then heat shield, thermal shield, and actually is going to be newly created as one of the possible options. So we keep an eye on those possible the reactions. Now, the final summary. The ITER project has the continued progression in most areas in 2022. The Tokamak plant and also the assemblies. Actually, we made a great advancement. For the Tokamak, actually, the second module has been completed, and actually, we're able to meet with the specifications. And as for the plant facilities and the cooling and the coil and the power, actually, it has been already completed, and commissioning has been started. So we made impressive progress. But at the same time, actually, we suffered from the thermal shield leak. Actually, we are going through the specific details of operations, how we can actually address these issues. Going forward, of course, we'll move into the full-fledged, actually first of kind, the based engineering issues and challenges, and of course, an architecture to come up to the surface and going forward. As has been mentioned by the Director General of the ITER, actually, it is going to be very important for us to further strengthen the relationship and collaboration among all the parties concerned, ITER industries and academia. So it's very important for us to actually go for such a collaborative environment. This is going to be quite critical. Actually, how we started our dialogues with domestic stakeholders. So I'd like to ask for your support and understanding going forward. With this, I'd like to close my report. Thank you indeed.
Thank you very much, Dr. Tada. At this point, I would like to introduce the guest of honors, Mr. Susumu Yamaguchi. He is represented by his secretariat. He's the House of...
Thank you indeed. Next, I'd like to introduce from the next R&D, actually, Fusion International Corporation strategist, Koki Inada, who is going to actually introduce some activities here in Japan.
Mr. Inada, please take the floor. I am Inada, Director, International Nuclear and Fusion Energy Affairs Division Mixed. I'd like to thank all of you who are here today for your continued efforts in ITER, BA activities and future R&D. We are very happy and we are really appreciative for your efforts. And also, thank you very much for taking your time to be here despite heavy rain. Today, I'd like to explain the research and development policy on fusion energy in Japan. So, in the first half, there has been a presentation by Dr. Tada, the Deputy Director General. And then after that, the further explanation, technical one, is going to be given by Dr. Takenaga. So I'd like to speak about what is taking place in Japan. So up until very recently, this was considered to be the technology of the future and technology of the dreams. However, things have changed. The Prime Minister Kishida, who took office in October last year, in 2021, the nuclear energy was included. So this has been mentioned not only by one individual, but also by several members. So there had been a discussion. And also at the election, nuclear energy, nuclear fusion was included in the policy platform. And then after the new administration of the Prime Minister Kishida was elected, after he took office in October last year, he stated certain things, including nuclear fusion energy, in his policy speech. So here, as shown here, research and development is being conducted in stages toward the realization of fusion energy. So I'd like to speak about this later. And then many people said that the nuclear fusion energy would be realized 30 years down the road. But then in the United States, they said that it would be the 50 years down the road. And then in that situation, they are able to understand what kind of the future and the kind of society in which this nuclear fusion is going to be implemented. But here we have after verify the scientific feasibility of the project. Currently, we are in the scientific and technological feasibility stage. And so we have this taking a look at it. And so this is the very much the theoretical figure, but we can safely say that this has been realized in 1980. It was considered to be a dream, but after 50 years of research, now we are able to see the scientific feasibility. That's the status at this moment. And then, but then we were thinking about the middle of the century, but again, the 50 years down the road had been considered. So if you're talking about 50 years down the road, many people said that these technologies would be evasive, but in recent years, R&D had been made for them. So that means that this is not considered a moving target, but rather this is a static target for which people will be able to work on R&D. And so at this point, we are working on the scientific and technological feasibility. So we are in this stage, and as has been mentioned, certainly this is a major and very complicated project, so it is not without the problems, but still we have a very good progress. So, and also we have good competition. And then in this competition, Japan is now working on it, and so we are now looking into the scientific feasibility and scientific and technological feasibility. And also at the same time, it is important to understand engineering background with which to realize certain goals. This is what we are doing at this moment. And please do understand that this is the blueprint or the roadmap that we have. And then this is about the ITER project. This has been agreed upon between the then President Reagan and the Soviet leader Gorbachev. And at the end of the Cold War, they talked about something that would take place in the years and years down the road. And then, so there have been many twists and turns along the path. And so in 2007, the ITER agreement was enacted. And then many things have happened ever since, but it still is very important. And many countries are looking into the future. This is agreed theory that this would be something that the entire human beings would have to strive for. And there are two things ITER is working on. And so when I said in 1998, the scientific feasibility was established in order to be economical. So this is about 300 to 500 euro. If it is in this area, then it is possible to continue operating this. So this is the economic feasibility. And also the 10 times more the output than input. That means that energy creation is possible if it is the case. So that's the kind of the feasibility that should be established. And another issue, many people say that it is possible, but many other people are saying, is it really true? So this should be verified. So this is a huge one. And so the construction is being conducted. And so relatively speaking, it is done in a proper manner and with good progress. And so in 22, they have been working on the assembly of the core. But many people are now making investment because the people are now aware of the fact that this kind of thing will be realized. So, but the invitation of investment from the private sector is of the essence. Japan has the technology and the expertise. Now we are in the midst of the competition as to whether to be included in this or not. On the other hand, so the QST will speak about this, but I'd like to speak about BA activities. So about half half of the population and one-third of the GDP are now participating in BA activities. So BA activities is about the sharing of the cooperation. So the ITER is about the cooperation. Japan and Europe are very strong in the entire world, and then it is not that these two the poles. Well, actually, this is that the Japan and the Europe will work hand in hand to start this kind of initiative ahead of others, and there could be three things. So ITER is about the demonstration of the actual operation. And so in that respect, a stable operation is of the essence. However, if you think about the smaller size, or if we are talking about economic cost effectiveness, in that situation, it is important to have the higher conditions. So this kind of the test equipment is needed, and then the HE60 SA is what is going to be done. And also, in the case of ITER, many people are participating. So for each country, it is impossible to do everything by one country. But in the case of Japan and EU, because of this, the EU is a combination of countries, but Japan is one country, and Japan and EU are now working hand in hand to work on this. In the case of ITER, and so ITER is the experimental reactor, so it is not generating power. So in order to have generation of power, we have to work on the neutron and the acceleration, and also we have to have the development of materials. So in Wakasho, Institute, they have been working on the research for the actual commercialization. And so I talked about the plasma. So in Japan, we have the large-sized helical system, and this is in the city. And this is very striking. This experimental device is about the observation of plasma. So it is very good. This is a very good experimental device. So in the case of plasma, in order to have the operation, it is important to have the good understanding of plasma. And we can safely say that this is a strength of Japan. And then having said that, the roadblocks or the enabling technologies should be combined with each other. And at the next, we have the strategy for the plan for the R&D. And so this is what we have been doing. Starting 2017, we came up with the plan for the promotion of the demo reactor. And so this was quite concrete in terms of the content, and this is called stage gates. What should be done up until then, and then what should be done on the next stage? What should be the content of what should be the kind of things that would be done in the next stage? So this has already been streamlined here. For R&D at least, we have the all Japan approach. So that means that this is the cooperation between industry, academia, and also government, and also maybe we would include banks. So this is the all Japan approach, and this is a roadmap. And so one point of the stage gate is for in the interim CR. So we have concept, and then on the second point, the first club, after the 2 years after the first plasma, we have the check and review. This is the interim check and review, and then after the conceptual design, we have to work on the engineering designs. So this is the R&D for the creation of detailed design. So the development should take place here, and then the DT operation Q equals 10 should be created here, and then we make a decision as to whether to move on to this area. So this is a roadmap at this point. The point here is steady and sturdy plans. Check and reviews are of the essence here. By conducting check and review, we would make decisions as to whether to go forward or stop it there. And then in the 2020, there had been the check and review system, the report. I we'd like you to see that. So looking at this, we can say that it is all in all the kind of things that has been done properly. So it is not about power generation. So in what way are we able to work on this? And also how we are able to work on the human resources development. And also the R&D had been the kind of things that the MEX is working on, but still we are not very strong here. So again, we have the discussion with stakeholders in the industry, academia, and also government collaboration stage. So here we have this kind of a forum, the Science and Technology Committee for Fusion Energy. So this kind of discussion would be reflected onto the plans. So lastly, I'd like to speak about the human resources development, training and securing human resources. It is not that the 30 years of the evasive. We have to make sure that we'll see the end point there in 20 years and 30 years. We have to say that this is worth 2 to 3 generations. So that means that the younger generation should come into this field. So it is imperative to work on the training and education of these people. We have to start with the graduate school education, and the support of many of you is important. It is considered to be relatively safe, but still the neutron is emitted, and also it is not free of the danger. So based on this, it is important for the public to understand and support that. Outreach activities are important.
So that is the work of NEXT, and now I'm the counselor for the Cabinet Office for Integrated Strategy, so I'd like to speak from that perspective. So NEXT is focusing on the R&D strategy. NEXT wants to do R&D as quickly as possible, and there are some limits. The Cabinet Office is different, so it has integrated innovation strategy, and its mission is to implement technology in society. And so for this strategy, of course, this is about the nuclear fusion strategy, not just R&D. And that's how it's discussing this. And in April, at the Integrated Innovation Strategy Promotion Office, it will be decided, as written here. And I'm going to explain what has been discussed and what will happen in the future based on the interim summary that has been published. So different from MEX, at the Cabinet Office, social implementation is most important. When you think about social implementation, there are many ways to do it, but the involvement of industry is important, is what we think. And so in terms of the direction of this study, well, this is number 4, because there has been a lot of discussion that preceded this. And so development of industry is the key here. So there is this cluster of technologies for nuclear fusion. There are general purpose technologies and specialized technologies. It's a wide range of technologies. And so each of the experts have a lot of knowledge about their field, but for neighboring technologies, if you ask them about that, well, the reactor designer may be exception, but the other experts cannot answer about the other things. And development strategy, maybe there should be a designer. But when you think about it as an industry, as a manager of industry, is it connected to your business? If you cannot see that, they cannot understand if they are connected to it. So nuclear fusion technology group. So we have to first show what the group of technologies are. So visualize is the first pillar. And also we rely on SMEs with specialized technologies. And even if it's a large company, maybe it's just one small department. So it's essential, but maybe difficult to maintain as a business. And so if they could fall if they are done independently. So they did R&D, they can now manufacture. But sorry, we don't have the we lost the capability to establish this as a business 5 years ago. That could happen. So even if it's a weak technology one by one, you have to connect and create a supply chain around it. And how to secure that supply chain is quite important. So connect is the keyword here. So it's not just connecting technologies, but the industry and different industry fields should also be connected. And also nurture, grow. You have to have that for the future. So that is what is going to be discussed. So R&D strategy. So not much different from next one, but when will it be completed? Nobody knows. And these new technologies. So there was that linear line earlier. The development model has been explained, but if you look at the elemental technologies, some are new technologies and some new surprising principles to be introduced. So what to do with these new technologies is one important factor. And so Kodak made the digital camera talking about destructive innovation, so it destroyed its own industry. So maybe the later technology may excel. So we have to check the new technologies. And also cost. It should not just be about R&D. We have to look at the cost viability and also what should be the organizational setup to implement that, and what should be the comprehensive strategy, looking not just at the part but the whole. So that will all be considered. And then what should be the organization in place to implement this? That's an important pillar. 2 points. So the big picture, I talked about the big industry strategy. Well, how can we have industry, government, academia collaboration and have a concentration? That's what we have to think about. So in the past, it tended to be the case that, and it could be said about the Fusion Energy Forum of Japan as well. But would management of small factories participate? Probably not. So how to broaden the range of participants is quite important, and that's what we will study. And so this is interim summary. And says who will consider. So this is who within the cabinet office. And then when you do the reactor design, what should be the organizational setup? You need a core project. And QST is an R&D institution. And so to develop this to a much larger scale and to create a demo reactor, we have to have a shift. So what to do there should be discussed. It could not be just done by R&D. How to involve academia and private sector. And so how to strengthen that kind of organizational setup is another point to be discussed. And then R&D promotion system. Well, so same as what I explained for the MEX, because we have the same awareness. If it's industry, it's 20, 30 years. So it's the time that a new employee will rise to president. So when you think about the current generation, I think you need to go through 2 or 3 generations. So with that in mind, we need to develop human resources. And especially about researchers, they don't necessarily stay with one institutions. And so how to have fluidity of human resources, how to secure human resources. And probably this cannot stay just in Japan. As I said, we have the technologies. So if we have infinite amount of funds, we could do everything domestically. Do we have infinite funds? Not so sure. So we have to really look at how things are progressing overseas and work together. So human resources, maybe we need to procure not just in Japan, but across borders. I mean, when you think about the geopolitics, there are some countries with whom you cannot work with. So you have to really think about, but like-minded countries, we should collaborate and have exchange of personnel. So that is another thing that we will consider. And also this kind of thing. Well, fortunately, energy issue is attracting a lot of attention. Power is expensive, it's cold, oil is expensive. So there's a heightened interest. And it's not a transitional thing. It's a long-term issue. And so consciousness about this field and the outcome should attract attention over the long term. And for that to happen, what can we do? What can we do? What that would yield? What that would create over the long term? So outcome and listening to stakeholders quite important. So create achievements and promote understanding of the people is something that we need to conduct. So at the Cabinet Office, we are discussing strategy. So going back to my dual position as MEXT and the Cabinet Office Counselor, so what do we need to do? First, for the short term, ITER and the BA, quite important. So we should steadily implement these activities. And from the mid to long term, we should do R&D and human resource development toward the demo reactor. How to do that is something we have to think about. Third, we should involve not just the R&D institutions or just industry. So we should create appropriate strategy so that we have an all-Japan system, plus partners overseas to have a grand strategy to work toward the dream of humankind to have the sun on this planet Earth. Thank you very much.
Thank you indeed, Inaga-san. Next, we'd like to have Dr. Takenaka Hidenaga. Actually, he's going to go through some of the important ideas and ask for the progress of the BN activities related to the ITER project and J1860 essay and proposal for the demo reactor. Without further ado, the floor is yours. Thank you again for the kind introduction. This is the Takenaga. I'm serving as the director for the NACA Research Institute. Thank you. Again, I'm here now to talk about the internal project as well as our involvement in the activities, what we call the J1860 essay, as well as demo reactor perspectives. As has been explained, and actually Japan's fusion research and development is currently focused on the ITER project, which is a large-scale international joint project, and the Japan-Europe international joint project, what we call the broader aspect activities, BA activities. At NACA Institute, we are actually is promoting the broader approach activities. Again, the J1860 is a part of this. So this is going to be actually the next phase. Actually, we'd like to start this steady the journey going for the demo reactor. We'd like to accumulate lots of insights and knowledge, and also we'd like to have them shared among all the people concerned. And in regard to the ITER organization, of course, we need to look into ITER project, and also we need to look into the J1860 essay. We need to be able to make sure that all these insights can be shared among all the people concerned. In regard to the J1860 essay, of course, collaboration with Europe is going to be quite important, but also we need to actually work on the better explanations, particularly within the USA and the recent issues. Actually, we started our specific dialogues. We are trying to deepen our collaborative relationship there. So international collaboration is going to be quite important. And going forward, as has been pointed out by many presenters, actually, we need to look into this in a new aspect of the international competition in this field of the fusion and energy. So this is another important aspect we keep an eye on. So we are looking into this international the competition, and here we need to look into the strength of the Japanese domestic industries, and we need to actually nurture them. So at the NACA Research Institute, actually, we are trying to actually encourage the broader participation from many people possible. We started making our efforts in this regard. I'd like to look into the ITER project at a deeper level. This shows the procurement the Japan is responsible for. The orange in color indicates superconductor toroidal on the field, TF coil, and also superconductive on the central solenoid, CS. And also now we have the 4 4 units out of the total 8 units. Actually, in 4 units, actually in the measurement, actually they are going to be necessary the measurements for the very first plasma. That said, in the past, actually, we made our procurement centered around this, the equipment devices, but actually, fabrication has been already almost completed. Also, has been completed, and as of now, we are looking into then actually the other devices and after the initial plasma. So I just wanted to share this information as to the status we have reached, and we need to look into the diverter actually in order to address the leakage of the heat, and also we need to actually protect the bronchite, and also the plasma measurement, and also we need to have the NB neutron and beam, the irrigation, and also the RF devices, and also we need to have the good facilities for the tritium plant. What you see here is the overall schedule of the ITER operation and also the Japanese procurement schedule. As Mr. Tada explained this to some extent, actually the overall schedule could be reviewed to some extent, but as of now, 2024 assembling is supposed to be completed, and also in 2025 the very first plasma is going to be operated. After this, actually we need to work on the installation of devices inside the reactor, and hydrogen and helium based operation actually at a low the magnetic field. So we would like to actually have this very first operation. Then we would like to move on to the heater aspects. So actually, the unit number 2 is going to be the device in question, and also in 2030, from 2035, and actually we would like to actually start the actual heating operation. And that said, as for the procurement on the Japan side, actually superconductive CS and also the gyratoran, actually 4 units needed for the first plasma. Actually, the assembling of these units have been already completed, and also the 8 plasma will be needing these units, and also the TF coil and others. Actually, we are in a really good shape actually in terms of procuring these the devices. And of course, for the initial plasma and after initial plasma, of course, we need to actually procure these sets of units, and actually we are moving into the full-fledged force-intensive procurement going forward. So I just went through the highlights of the Japanese procurement, and here it's important for us to have really good collaboration with the industries. So it's important for us to disseminate information concerning the ITER project and also what we need to have. So we would like to actually be quite strong and the information the sharer in these regards. That said, actually progress of procurement, and I'm going to introduce the video to you here. What you see here is on ITER construction, overall construction site. That's what you see here. And TF coil, as of now, actually 7 out of 9 units actually have been completed, and also the delivery has been completed. And as for the structures, of course, including structures to be delivered to Europe, the actually 19 units have been already done. At the ITER site, of course, the assembly is well underway, and also the TF coils, and 2 of them actually the Korean made the vacuum the vessel, and the other units have been already installed. And of course, in 2024, we are supposed to actually TF coil procurement actually by the end of 2024. And Japan is responsible for the gyratoran. Actually, 8 units have been already completed in terms of the fabrication, and 2 out of them. And January 2022, actually delivery has been done. Actually, they have reached it on the site, and by the end of 2024, all the gyratoran actually transportation is supposed to be completed. And as for the instrumentation, this shows just one example. This is a neutron microfission chamber. How we are making it, and actually Okazaki says action, this is one of the action companies here in Japan. Actually, we have good collaboration with this company. Actually, we actually developed the new plating technologies, and actually we got a patent out of this. And 2022 in April, actually based upon this technology, and actually we have built this signal cables. Again, Japan, of course, is behind this procurement. And actually, this is the very first unit actually based upon our the expertise and delivered to the ITER. Next, diverter. And the leaks, leak and heat and others actually from the plasma actually need to be processed. This Allied Materials, Yamato Gokin, and Kinzoku Gokin. Actually, three companies actually behind this in collaboration. And 200,000 units on tungsten tile actually for that to be made. Again, this is a production line. It's now in operation. Actually, and speed is 8x the increase. And ITER organization is going to be responsible for the heat testing, plasma unit, and actual resistance unit actually is well underway. So, of course, we are making a really good preparation for testing, and also the neutron beam procurement, and actually it'll be actually real the experimental space selection. Actually the overall integrated test is underway, and back in 2019, and Mexican actually the Vice Minister Miss Nagaoka actually was a part of this the mission to the site. Moving on, again, I'll go through this to the yellow field, TF coils. Several points, and actually, Japan is responsible for the 9. Actually, 6 out of them actually have been delivered to the ITER site, and 2 by the Korean made. Actually, that should be a part of the vacuum reactor sector. JT16SA actually knowledge is going to be quite important. Actually, we're helping actually from NECA researchers and ITER and JT60. Collaboration is well underway as shown in this picture. ITER and also JT16SA. Actually, we are actually successful in sharing the technological capabilities as well as insights. And the 7th unit, it is now being transported through the ocean. It has just reached the port in Europe. I'm so happy having received that information. And 8th unit, again, it's in the final the fabrication and supposed to be completed by the end of this fiscal year. As for the spares, actually, they are supposed to be completed sometime next year. So we are in a really good shape, and the Mitsubishi and Heavy Industries and also Torsby Energy and Systems actually they are helping us. Actually, we are truly having a really good level of collaboration, and we will see to it that no problem is going to take place. Here now we are looking into the radio frequency heating system. Actually, 8 units have been already fabricated, and in this year we're talking actually 170 gigahertz, and also the 1 megawatt on higher, and also 50% efficiency are required. Again, on the they are supposed to be completed within 300 seconds. We are now conducting testing, and unit 1 through 6 have been already certified. We are now working on the testing of the 7th unit. And furthermore, the very first unit actually low the magnetic field in operation, and with that point in mind, actually low frequency is going to be one of the developments, so we need to keep an eye on. Again, we are going for that capability. It's just been announced in the press. Actually, 2 frequencies are mentioned here, but actually with this latest development, actually 3 frequencies are going to be also covered. And Canon the tube device, the person is going to actually explain this matter. Next, diverter side. Diverter actually then heat coming from the plasma and also the quantum actually. So the system needs to be strong enough and actually against such a super hot environment, 20 megawatts per square meters, as you see here. So melting point, and actually tungsten has a high melting point. So tungsten monoblock and actually 200,000 units are supposed to be made. There will be Allied Materials, and actually is going to make a presentation actually covering this. So the mass production line actually has been already prepared, moving into the mass production. And in the center, what you see then special copper alloys, the pipes. Actually, with this, we're going to actually cool down the temperature. Yamato no Goking actually is making this, and that is going to be actually plated with wax. And then heat from the plasma needs to be avoided. Again, between the tiles, actually the gap here is going to be 0.4 millimeters. This is going to be quite a tough specification. But as for this, as Mitsubishi Heavy Industries and Hitachi, actually manufacturing actually are behind this in order to actually establish good technologies in order to meet with this gap specification. Moving on, and neutral beam injection heating system, and 1 million volts and 14 amperes, and actually the negative ion beam. Actually, we started developing this accelerator, and negative ion needs to be extracted, and it goes to the rather complex environment. Again, the electrodes and also the poles need to be made, and again, a short distance, and actually the insulation for the short distance is going to be quite needed. So we need to develop this rather complex 3D geometry. Asahi, the Kinzoku, and also the engineering actually are behind this effort.
So in the case of ITER, we have been enjoying the participation from many parties. Now let me talk about JT60SA. JT60SA is working on the research to support ITER and to complement ITER. So as can be seen, the target area includes the sustaining high-performance plasma for about 100 seconds, which is necessary for demo reactor to achieve the high power output. And furthermore, we will provide a place for human resource development. We will train young researchers in JT60SA and develop personnel who can lead ITER experiments. That's how we are looking at it. This is the status surrounding JT60SA. We have suspended the integrated test operation since the insulation failure that occurred in March 2021. And then we strengthened the insulation at more than 100 locations with similar structures or similar locations, as well as the location where the failure occurred, because we were able to understand that the insulation was not strong enough in these areas. After the work was done, the strengthened areas were hooded to create a pressure that would facilitate discharge, and we made sure that the discharge was not observed. So this is called local passion test, and the local passion tests were conducted for each area to confirm that the areas still did not discharge. In July, we were able to complete this kind of a process. And then in August and September, the pressure in the cryostat was set to 1 to 1000 PA. And this is called the global passion test. And so this is the overview of, or the illustration of the configuration. So we made sure that this is conducive to the discharge. So the pressure in the cryostat was set to 1 to 1000 Pascal, which is the pressure at which discharge is likely to occur. And so this is from the 10 to the first and 10 to the negative 5 the Pascal. But if in the case where there is a vacuum leak, and then that is considered to be abnormal situation, but we are prepared for that. So this kind of global passion test was conducted, and then we decided that for some part, some insulation is needed. So we are in the process of working on it. By the end of this year, we will complete this process. When I say by the end of this year, this is within a week or so. So we can safely say that today or maybe tomorrow we'll be able to complete the process. So this is the staff in charge of ITER superconducting coils provide support for insulation strengthening, and meetings are held regularly to share information with the ITER organization. This is example of the sharing of knowledge and technology and also human resources between NACA and also ITER. So we can safely say that this is a very good example of the collaboration between ITER and JT60SA. This is the schedule of JT60SA. This is a schedule agreed between Japan and Europe at the BA Steering Committee meeting on December 15th. The insulation strengthening work will be completed by the end of this year, and then the global passion test will be conducted at the beginning of the year in January. Once sufficient with the voltage performance is confirmed, then coil cooling will begin. And then after confirming that cryogenic conditions have been reached, the withstand voltage tests are conducted, and then integrated test operation will be conducted from the coil energization test. And then at this point, first plasma is expected in the middle of 2023. After fall, we plan to increase the equipment power for maintenance and heating experiments. So this is the schedule we have at this moment. Then this is the main body equipment. Allow me to show you a video. So, as part of the equipment expansion for the full-scale heating experiments planned after the integrated test operation, we are currently expanding the common stages that surround the main body of the tokamak. And so, for this, we have these stages will be used as workspace for the enhancement plan. Will also be used for the placement of new instruments and equipment to be procured in Japan and Europe, as well as the adjustment and maintenance of the equipment. Here, this is the superconducting coil equipment. JT60SA uses superconducting coils with zero electrical resistance. Here we have the tube, and this would go into this JT60SA. And this is the helium path, the cryogenic helium path for JT60SA, the main equipment. So this is the main equipment that you are seeing here. Next is, well, this is that was the path for the cryogenic helium to the connection of the superconducting coil of JT60SA. This is power supply unit. This section describes the power supply system. This is a high power supply system that supplies the high DC power required for plasma experiments to the superconducting field cost. It consists of effectively reusing the existing JT60U power supply facility and combining it with new power supply equipment procured mainly in Europe. And then this is a heating system. For the RF heating system that heats the plasma, we have succeeded in developing an oscillator capable of outputting 1 megawatt at 3 frequencies, and now ready to inject up to 1.5 megawatt of RF power into the tokamak for the first plasma. And we are now collaborating with Europe to conduct the experiment. And this is a blue tank. The blue tank in the foreground is the world's largest negative ion source neutral beam injector, and also the neutron beam injector, and then there are 12 positive ion source neutral beam injectors. Large-scale restoration work in the JT60 main building will begin in the next fiscal year. And this year, we are restoring the drive unit for the calorimeter, which is used to measure the beam. And then this is the measuring device. And this is the largest instrument in JT60SA, which measures the electron density and the plasma. And we are conducting experiment on this measuring device as well. And then this shows a calibration experiment using the laser before installation in JT60A. This is a tracer palette device to measure the behavior of unwanted impurities. And since some of the instruments are to be procured in Europe, we are working closely with them using the web conference. And finally, I'd like to speak about general control system and control room. The JTS60SA is operated under a supervisory control system, which is a monitoring system that is linked to all the facilities that make up the device and is used to develop advanced control logic for controlling the fast and complex behavior of the plasma in real time. And what you see now is a control room where researchers and engineers gather during experiments. So as can be seen, we are in the due process of the preparation for the heating experiments and also integrated experiments. While we are proceeding with the work to increase the power of the device for the heating experiment in this way, we have also started discussions on the content of the experiment by forming an experimental team. 2 Japanese and 1 European experimental team leaders have been chosen, and the topical group leaders have been selected, and the experimental team coordination meeting is being held. And then they are now discussing what kind of experiments should be conducted. And then we have the universities and other organizations in Japan are expected to participate in the core plasma joint research, and several universities and other organizations are expected to participate by concluding on-site laboratory the collaboration set up at Naka's Institute. And also, in addition, the holding of the Nuclear Fusion School for Human Resource Development will also be discussed between Japan and Europe, and is scheduled to be held in the fall of next year. And here are some examples of efforts to promote industry participation. At Naka Institute, in cooperation with Ibaraki Prefecture, an attempt was made to conduct technology matching between companies in Ibaraki Prefecture and Naka Institute. So we are providing information to the companies about ITER and JT60SA, and also they are exhibiting their technologies at a company booth and deepened exchanges with researchers and engineers. So we heard that there are some cases that quickly developed into business negotiation. We'd like to see that happening in the months to come. And also we have created a map to see what is being done. And finally, I'd like to speak about human resources development. To build a solid foundation for demo, it is important to develop people. To this end, we are utilizing JT60SA and ITER, and we are in the process of creating All Japan framework to foster and secure human resources by increasing the mobility of human resources. So this way, we are able to work on the creation of the foundation for human resources. This is a summary page. Regarding the procurement of ITER equipment, we have reached the stage where we completed the procurement of equipment required for the first plasma, and the procurement of equipment required for operation after the first plasma is in full swing. The JTS60SA project is scheduled for first plasma in the middle of 2023. Increasing the power for subsequent heating experiment is now underway. Specific details of the experiments are being discussed by the experimental team, and therefore I believe that there will be even more importance to promote participation from industry to train and secure human resources for the demo reactor, and we'd like to continue working on this with the All Japan approach. That's all for me. Thank you very much for your attention.
Thank you very much. We now have the Director of the Fusion Reactor Materials R&D Department, Yokkasho Research Institute, QST, Mr. Hasegawa Kazuo. He will talk about development of high-power accelerator in BA activities and expansion to industrial applications. Mr. Hasegawa, please. Thank you for the introduction. I'm from the Rokkasho Research Institute. My name is Hasegawa, Director of the Fusion Reactor Materials R&D Department. Thank you very much for this opportunity to present. I'd like to talk about the development of the high-power accelerator, what it is, why, what we are using it for, and how it is applied to industry. This photo is used in the flyer, and it shows the prototype accelerator, the LEPAC, which I'll explain today. You supply energy with radio frequency waves to the accelerating cavity called the RFQ. Radio frequency waves, I think you're familiar in terms of the RF signals. What you see is the waveguide that supplies the radio frequency wave to the accelerator. To give you an idea of how strong this energy is, we can put 200 kilowatts into one unit. The output of the terrestrial digital radio wave emitted from the Tokyo Skytree, which is celebrating 10th anniversary, is 10 kilowatt, so it's 20 times that. There are 8 such units, 4 in the front and 4 in the back, for a total input of 1,600 kilowatts. That is an astonishing 160 times the output of terrestrial digital broadcasting to realize the world's most powerful accelerator. The purpose of our research and development is to realize power generation by nuclear fusion. To demonstrate the prototype reactor. In a fusion reaction, a large number of fast neutrons are produced and the energy is converted into heat to generate power. On the other hand, these neutrons hit the inner walls of the demo reactor, possibly causing the materials to become brittle and deteriorate. Currently, a promising candidate material is reduced activation ferritic steel developed in Japan, but it's necessary to conduct durability tests against neutrons. Therefore, an accelerator will be used to create neutrons and conduct validation before the construction of a fusion reactor. This video explains the development of materials to realize fusion and why an accelerator and LEPAC are necessary. The Rokkasho Institute is developing the most powerful accelerator device in the world. What kind of device is it? The demo reactor is a plant that will generate electricity from nuclear fusion energy for the first time by humankind. It is uncharted territory that no one has yet completed. A major obstacle to the completion of the demo reactor is the impact of the extremely high-energy neutron particles generated during the nuclear fusion reaction hitting the walls of the reactor. We must develop new unknown materials that can withstand this shock. And the project to develop equipment to verify these materials is the IFMIF EVEDA project. There are 2 steps to developing materials for the demo reactor. First step, the neutron impact to test the materials must be reproduced. To do this, a prototype accelerator is built to accelerate high-power deuteron particles to a high-energy state with very high velocity. Second step, build a neutron irradiation facility where the prototype accelerator will be installed. The accelerator will produce neutrons, which will be irradiated onto materials to verify which materials are suitable. Using the materials developed here, a prototype reactor can finally be built. Here at the Rokkasho Fusion Institute, we are developing a prototype accelerator for step 1. In other words, we are developing the most important device that will lead to the development of materials for the demo reactor. The name of the accelerator is LIPAC. The completion of LIPAC will truly accelerate our energy future. The development of LIPAC, the world's most high-power deuteron beam accelerator, will lead to the realization of a nuclear fusion reactor. The main feature of LIPAC is that it can continuously inject large number of particles than conventional accelerators that intermittently injects beams. How does LIPAC produce such an intense beam? Let's take a look at the beam acceleration process that brings together the most advanced technologies. First, deuterium is filled into the device and microwave is used to turn it into a plasma state and produce particles. The number of particles produced is 10 times greater than an ordinary accelerator. The particles are pulled by voltage and are injected as a beam from a device called an injector. The particle beam flies and finally enters the first stage of acceleration, the RFQ. The world's longest RFQ at 10 meters is continuously injected with several hundred kilowatts of RF power. The inside of the tunnel is sandwiched between electrodes from 4 sides, and the gap between the electrode is only about the size of a human pinky finger. There, an electric field is generated with a frequency of about 200 million vibrations per second. When particles enter the tunnel, they are focused up, down, left, and right, and accelerated like surfers on the waves of the electric field. The particles increase in speed, and by the time they exit the 10-meter tunnel, their speed has increased 7-fold. Next, the particles pass through the second stage of acceleration, a device called a superconducting accelerator, which can create a strong accelerating electric field with a small amount of electricity. Particles are rapidly accelerated in the instant they pass through this cavity. After the acceleration is repeated 8 times, the speed increases 10-fold from the exit of the injector, reaching 10% of the speed of light. It's a speed that can circle the Earth in about 1.5 seconds. Finally, it is caught by a special device called a beam dump. When completed, LIPAC will be the most powerful accelerator in the world. Now, we'd like to see the prototype accelerator LIPAC together with local high school students. Local students from Rokkasho High School visited the front lines of research on the world's most powerful accelerator device in Rokkasho Village, Aomori Prefecture. Today, we'll be filming these local high school students asking questions of Dr. Akagi, a researcher who works at the site. This is the first time for them to enter the lab. How does it feel? I feel like I've become a researcher. And finally, they come face to face with the accelerator. What does this device look like? Is it some kind of engine? Now it's time to start filming. Both of you, ready? What does this accelerator accelerate? This accelerates particles called deuterons. The purpose of this device is to accelerate deuterons with the world's largest current and to develop an accelerator for a high-power neutron source, which is necessary for developing materials for future fusion reactors. Where does the beam go? The beam is first produced in the injector, and then it is accelerated in the RFQ device. Then the beam is transported while converging using these electromagnets. Many detectors are installed in this area to measure the state of the beam, and the beam ends up behind the wall. Finally, the beam is received by this beam dump. What is that sound? This is the sound of a device called a cryopump working, which removes the air remaining in the RFQ. The accelerator was sitting close by, but you didn't know about it. Its principle is a bit difficult, but there are still many more fascinating things about it, so please come visit again. I hope you enjoyed watching that. This figure compares the performance of the world's major proton and deuteron accelerators, including LIPAC. The horizontal axis is the beam energy, and the vertical axis is the average beam current. The high-energy accelerators are used for nuclear and subatomic particle experiments, while the intermediate energy ones are used for material and life science research. Here is the LIPAC and the fusion neutron source, and you can see that the energy is not so high, but the average current is an order of magnitude higher than other accelerators. We are thus challenging the unprecedented high current regime. I list 3 challenges to achieve this high current. The first, needless to say, is we have to generate and accelerate high current beams. For this purpose, we need an injector that produces high current particles and RFQ to accelerate them while maintaining high current. And a high power RF source to give energy to the beam is also necessary. All of these are necessary, and we have developed them. Secondly, as shown in the video, it's necessary to accelerate the particles continuously, not intermittently. And in this case, with continuous operation, heat generation becomes a problem, so we invented structures and techniques to solve those issues. The problem of heat generation in continuous operation can be solved by using superconductivity, a phenomenon in which electrical resistance is reduced to zero when a special metal is cooled to near absolute zero. Also, we have incorporated controls to increase cooling capacity and to follow temperature changes. The third is to control the beam spread well. The accelerating beam itself has positive electricity and so has the power to repel and spread, so we need to converge and accelerate. As the current increases, positive electricity becomes larger and the repulsion becomes stronger as well. So to suppress that, a strong convergence force is applied to achieve acceleration and transport. For this purpose, advanced beam particle simulations were performed from upstream to downstream to optimize the convergence mechanism that strongly focuses the beam to achieve a loss-free design. Since the goal is to accelerate the world's highest current, the development of LIPAC has been done in stages. After a standalone test of the injector, an acceleration demonstration of the RFQ was conducted in 2018 to 19 using a low-power beam dump to demonstrate the acceleration of the RFQ. As a result, we succeeded in accelerating the pulse to world's highest current, 125 milliampere peak deuteron. And currently, we are conducting beam tests aiming at continuous operation by connecting the beam transport system and the high-power beam dump behind the RFQ. The result of this test, the beam current waveforms from upstream to downstream, are shown. You can see that's pulsed operation, but it shows that almost 100% of the beam is transported from the downstream of the RFQ to the dump without any loss along the way. Going forward, we will adjust and test the system for continuous operation. And as a final form, the beam transport system will be replaced with a superconducting Lignac to demonstrate the acceleration. For this purpose, we are currently assembling the superconducting acceleration cavity and preparing to install it in an enclosure called a cryo module, which will be installed in the beamline.
This shows the overall repack systems. Actually, the flags are shown here. The procurement is going to be done by Europe and Japan. But when it comes to the adjustment, we're supposed to actually have the joint adjustment and the beam testing. Again, on the Rokkasho and also the Europe, and actually, we have the remote data transfer system. Actually, in 10,000 kilometers in distance, and it can be covered in exchanging data. In other words, we can get to know what is going on in Europe. Actually, going through having the video conferencing room. So I think we are having really good, the strong teamwork in that show. The injector is one of the keys to the overall performance of the accelerator. Actually, as it cannot accelerate more than the current generated by the first injector, the performance required includes not only the current but also the convergence and stability and the longevity. The ions produced here are extracted from the beam, which can be observed as an illusory blue light, quote unquote. We have been vigorously developing the performance improvement of this injector. This figure shows the result of the long-time operational test. As a result, the injector was successfully operated continuously for 11 hours at a current of 150 milliampere. 11 hours, 150 milliampere. The injector has the target current of 125 milliampere. The high current required for the continuous deuteron beam acceleration test, stability, and convergence. The injector also achieved the target current 125 milliampere required for the continuous the deuteron beam. This figure shows the relationship between the RF of the acceleration cavity and the RF source. The RF is supplied with 200 kilowatts of power generated in the power supply room for the 8 RF units to accelerate the beam. The picture shows the actual RF for the source waveguide and RF in the process of assembly. The RF and RF and the source have a challenging performance for the world's largest current. The RFQ and RF source have really have to go through these challenges. 5 MeV and the highest current 125 milliampere. In order for us to realize this, actually, we have to work on the optimized convergence and the acceleration. And we have come up with a 9.8 meters. Actually, this is the longest. The RF source is a single unit with a power output of 200 kilowatts, and all 8 systems must be injected at the same time. The RFQ input power is 615 kilowatts, and during beam acceleration, it can be as high as 1,400 kilowatts. So these numbers are going to be quite important out of development, and we have a developer. Actually, input and current is 615 kilowatts again, and then 1,400 kilowatts. It is as high as 1,400 kilowatts. Here is the comparison of the energy and the average input power with other RFQs in the world. Currently, we have achieved 410 kilowatts, which is still the largest in the world, but we are working towards our goal up to 650 kilowatts. So we're going to make such continuous efforts. Here now I would like to share with you the enthusiasm of the European and Japanese researchers who are at the forefront of research, as well as a message from the European neutron source facility for accelerator and neutron sources.
LIPAC is a project between Europe and Japan. I've been working in this collaboration since many years now. And I can feel that we are progressing every day in a very nice atmosphere, and we are able, I guess, to overcome all the difficulties that are presented.
LIPAC is totally different from other accelerators. Actually, in working on the project, of course, there are challenge difficulties, but this is going to give us good and academic advantage. So out of this collaboration between Japan and Europe, we should be able to make a further advancement. We are hoping that we can leave the really good results.
Dear friends and colleagues in Japan, this is a greeting from all your friends and colleagues at European Spallation Source in Lund. We wish LIPAC all possible success with producing high-energy neutrons. We look forward to have you visit you and collaborate in the future.
Development to a neutron source facility for materials development. The prototype acceleration LIPAC for the neutron radiation facility has been developed between Japan and Europe. As a next step, now we are planning to develop a fusion neutron source facility. We call it AFNS. So this is going to be the next step. Again, this is a facility that can use a high-intensity neutron generated by an accelerator not only for irradiating the fusion materials, but also for various other neutron applications. The facility will not only irradiate fusion materials. We have completed the conceptual design, and we would like to move into the process where we can make a construction and also we can acquire data. This shows just one example. AFNS being a main building, and also the lithium target loop for the neutron production and the material irradiation module are in progress. The neutrons out of this is going to be 10,000 times in terms of power compared with the traditional the neutrons. So using that, we wonder whether or not we can actually find really good applications. One such application is going to be development of a clean RO production that does not require a nuclear reactor. Molybdenum 100 very thin capsule can be placed in front of the system, and the molybdenum 99 can be made. It can be used for the technetium 99, the most widely used material in nuclear the medicine diagnosis. But this molybdenum 99 is the most widely used technetium 99M in nuclear the medicine diagnosis. So the stable supply of this molybdenum 99 is going to be a major issue. So AFNS neutron research was conducted, and actually we should be actually producing 2x over the demand here in Japan. As shown in here, again, so far we have 100% dependence when it comes to the molybdenum 99. But now we may be able to actually make this domestically here in Japan, and also we can actually deliver the stable supply. This will pave the way for the domestic production and the stable supply of materials that have been 100% dependent on the overseas imports, and will enable the facility to be used simultaneously for material irradiation and medical the radioscope production. They are just some examples. We are truly hoping that we can find a lot more applications going forward. For example, the agricultural research and its application, and also semiconductor and like materials production, and advanced the healthcare and medical research activities, and also X-ray based operations utilizing the neutrons. We should be able to actually go deeper inside the organization of the bodies for the better the analytics. So we can go for these varieties of applications. Again, AFNS, the neutron facilities are in the center, and we're hoping that we can actually go for all these possible the applications. This is what we call the neutron forest concept. Now we have the message from the industry. I have high expectations for the production of the medical alloy using the high current accelerator derived from the research for an fusion of the neutron and the source. I have high expectations in this regard.
これは六カ所研究所
This
周辺の
shows the vicinity of the Rokkasha Research
この研究
Institute.
所に隣接する形で
And in the neighbors, and actually we are having AFNS to be built.
先ほど申し上げたような
And as I have explained, actually in the neutron, on the based research activities and also its applications, facilities are going to be built in the form like a forest, and what we refer to it a neutron forest. For R&D activities, we are hoping that this site can be fully utilized. Again, I'm part of this, and I'm going to make further efforts going forward. Thank you again for your kind attention.
Thank you very much, Dr. Hasegawa. This concludes. Well, at this point, allow me to introduce the guest of honors, Mr. Hiroyuki Miyazawa from the House of Representatives. Thank you very much. This concludes the keynote lectures. We will take a short break now. The next program, special lecture, will begin at 10 past 4. Please return to your seats by 4:10 p.m. Thank you for waiting. At this point, we'd like to start the second half of the annual symposium on the ITER project and BA activities 2022. First is a special lecture. I'd like to introduce today's speaker, Dr. Shigeyuki Nakaji. Dr. Nakaji was born in Nagasaki Prefecture and received his medical degree from Hirosaki University Graduate School of Medicine in 1983. He is a member of the Department of Hygiene and Preventive Medicine, Hirosaki University School of Medicine, where he specializes in a wide range of fields, including cancer epidemiology, sports medicine, and public nutrition. In 2012, he was appointed Dean of Hirosaki University Graduate School of Medicine and Dean of the School of Medicine, and in 2013, he was appointed Director of the Center of Innovation COI at Hirosaki University. He's also the President of the Society of Physical Fitness, Nutrition, and Immunology. Today, he will give a lecture titled Social Innovation for Health Promotion Utilizing a Big Data Platform. Dr. Nakaji, please take the floor. Thank you for your introduction. Good afternoon, ladies and gentlemen. I am from Hirosaki University, Aomori University. Please take a look at these shoes. And it has been snowing heavily. And also there is a Rokasho in the place called Rokasho in Aomori. It is not that we are visiting that place frequently, but we are learning a great deal from them. Now, I'm sure many of you are wondering why I am here. Why is it that it is related to ITER? But I do not worry too much about it. So I will speak to you about the kind of things I do, and this will be of some assistance to you, and then that will be a great situation. So this is about Aomori Prefecture. The Aomori is a prefecture with the shortest lifespan, and I said it is said, but it is actual fact. And this is the life expectancy ranking by prefecture, and every 5 years it is announced. Maybe because of the COVID, there could be some delay. This has been announced every 5 years, from the 1965, and the year Heisei 27, which is this is the 11th, and then the highest ranking is shown to be Nagano Prefecture, and they have apples, and we have Aomori apple and Nagano apple. Certainly, Aomori apples are much tastier, but some people say that this might not be very good for the health. So whatever the case, but in the past, Okinawa was the number one. And then at this point, we are seeing the decline of the Okinawa Prefecture, and we will see this, the number 35 for men and number 8 for women. And the people always say that this is an issue of the healthy lifespan. The healthy lifespan is the most important, but again, the kind of the health lifespan submitted by the national government is not very accurate. And then, for example, in the case of the Akita Prefecture, it was number 5, and then the next year it was 35th. And then, in the case of men, it was the other way around. So this should not be the actual reflection of the actual situation. So when you say the healthy lifespan, it is sometimes very difficult, if not impossible, to calculate. So I think it makes sense to look into life expectancy, and this is a reflection of the healthy lifespan. And then when I say that, I receive letters of the criticisms saying that if a person is bedridden, does it mean that that person is not happy? Now, let's come back to this. So this is the 80 years old and also 82 years old. And so this is not about 80%, 82.5. And then this is the comparison between the male population in Aomori and Nagano Prefecture. And so this is the mortality rate for this kind of bracket. The mortality is about number of people who die in the 1 million. And then in the case of the Nagano, the Aomori, it is 1.1 4 times. So 153, and then this is the Aomori. This is 153 versus the 109 in Nagano. So this is 1.5 times larger than that was Nagano. So this is the difference is the 3.6 years of difference. So if there is a difference of 1 year, and so that is a huge difference. So in what way are we able to deal with this? So I think this is worth a Nobel Prize if we are able to achieve this. And if we are able to change this picture, then this will lead to the change of the society. When I say when we look at the age bracket, all the brackets are dying early. So over the age of 40, many people are dying from the 3 major lifestyle-related diseases: cancer, heart disease, and stroke. So, and also lifestyle-related diseases have a latent period. In the case of COVID-19, 3 days. And then for the people to develop lung cancer, after they smoke, the 30 years would have passed. So that means that lifestyle-related diseases have a latent period of 20 to 30 years or more. So that means that it is important to see the change from early age. So if you try to work on the analysis of the average life, we are able to learn something more deeper into this. So with what kind of diseases they die: malignancy, which is cancer, the heart, and stroke and pneumonia, and for the people are dying with almost all the diseases in Aomori Prefecture. And then why is that the Japanese people they live longer than the most of the people in the rest of the world? So in Japan, many people are not dying with the diseases. Japan had the higher percentage of strokes. It was about 5 times that was the developed countries in Europe and the United States, but it is about the same now. So that means that because of the very low rate of the death and the mortality with malignancy and others, it had been delayed. So we can safely say that in Aomori Prefecture, people die of many diseases. Then let's take a look at the health-related indicators which are related to health. For example, smoking rate, and also drinking rate, salt intake, vegetable intake. Aomori's score is lower. Well, actually, Nagano is not very good. Salt intake is higher in the Nagano Prefecture. So Nagano is free of the waste. So I think they have been utilizing the pickled the vegetables and pickled the salt and salty fish. So I think we have to say that there is a major difference in the entire society's strengths. So maybe because of the salt intake, the Nagano Prefecture is not very good, but for other indicators they are good. So that means that they are number 1. Then what kind of things can we do? So we have to say that the Aomori Prefecture is the shortest-lived prefecture in Japan, 2.5 years difference from Nagano Prefecture. And so if you calculate, it's like this. We have 1.2 million people, and then they go to Nagano Prefecture, and then we will see the decrease of number of deaths by 2,800. So what is a figure of 2,800? So in Aomori, the 180,000 people die, and then if you reduce this, if you calculate this 2,800 divided by 1,800, it means that it is 15%. 15% more of the people are dying, and then looking at the Nagano and also Aomori, that's not different. So I have to say that the society's structure is different, and also people are not paying too much attention to the lifestyle of the disease. So the old ages are more likely to die, especially men in their 40s, and also high mortality from all diseases. And we know the reason here. The background here is the bad backside drinking over 2 goals, and the smoking and lack of exercise, the salt intake, and also low health checkup rate. And also they do not go to the health checkup, and also even worse is that many people would go to the hospital and when they are diagnosed with cancer, they are likely to be in stage 4. They are not able to be saved. And also, they go to the hospital when they have the advanced diabetes, so they have to have the dialysis. They have to go to the hospital 3 or 4 times a week. So that means that healthcare cost is very high in Aomori Prefecture. So this is the overall structure of Aomori Prefecture. Then what can we do? It's easier said than done. But we are talking about the structural issue. So we try to intervene here. We are now working on how to solve this issue. First is to have the improved health literacy. This holds true with many things, but everything should be communicated to the general public, and then after a while they will understand what it is, and then after that people start to change their lifestyle, and the health promotion is also the same thing. So what is done in Aomori Prefecture is shown here. Health promotion does not exist in isolation. It doesn't make any money. It is not glamorous, and it is the difficult task. So not too many people are working on the health promotion, and also not too many people are gathering around this. If it is impossible to see the gathering of people, it is impossible. The momentum is very important, but I think health promotion should become a central theme of regional revitalization. Not too many people are able to make the large amount of profit, so the major theme should be health promotion. And the third item here is that all industry, government, academia, and citizens need to become stakeholders. The doctors would not be able to do anything without the support of others. They have to provide the support to the schools, and also CSR should be conducted by the businesses. So here, the most important is the industry, government, academia collaboration. Many people use this term. Certainly, people can gather around the table, but it is impossible to bring about something without the common theme. But as can be seen here, many people have different interests. Companies would want to have the profit. It is not anything bad. Without the profit, it is impossible to have the survival of the company. CSR is also important, but still profits should come first. In municipalities, we want to have the medical cost control. Universities also are thinking about researches, and the citizens want to have the health promotion. They are looking at different things, and then they have vested interest, and they have hierarchies. So it is impossible to come to a conclusion. That's the reason why we are not able to have anything done. This is not only about health promotion, but also for other things as well. So the platform is important. So we decided that we have to create some very attractive platform. So this should be a honey for the bees. So we decided to come up with the big data platform, which would attract people's attention. Now, before thinking about this, let's take a look at the overview of the support of the people. So I am paying the attention here. This is the first priority. We have 40 municipalities, and for all of them, they declared the health declaration. And also, 1/4 of the schools are conducting health education. Frankly speaking, the systemic education are not conducted at the schools, so they would have the health product when they are grown, but they are not able to learn from the early age. And also we have the health management certification system, and this is what we call the health declaration by the mayor of all municipalities. So the mayors would declare that the municipality has the health declaration in front of the public. So by doing this, why is it that they are doing this? Well, actually, I think this will lead to the higher votes. So we have to have some incentives. So if you are saying the causes, it doesn't, or the good things alone, it doesn't lead to anything. So it is important to raise the hurdle and raise the bar. And if they go beyond that, then in that situation, things would change. So that means that many people are doing their own things in their own interests. But here, it is important to have the top management here, the IE, the mayors who do things, and also volunteers. There are many volunteers, but the heads of the municipalities are there to look into this. So this is really about the intellectual level of the municipality leaders. And also we had the education board, and when the municipality leaders say they have to do certain things, and the schools will follow. So this is the structure of the schools. So this is the systematic approaches of the education of health for the elementary school and junior high school. So this is about how they have to think about health. And then there is the word of mouth. So they are in their 40s and 50s. We are not able to have a good reach for them, but through the elementary and the primary this school, these students, they are able to receive information. And here we have the wide industry, and back in the past it was impossible to have this kind of discussion. We are talking about the health promotion, and not too many people are interested. They were the university professors are saying certain things, and this is just a dream or a pipe dream. And then now many of the schools, many of the companies are trying to be white rather than black. So in the case of the Aomori Prefecture, they are trying to certify the health promotion and health management to the companies. Why is it that the Nagano Prefecture is doing well? But we have to say that there are many people who want to intervene. So there are the 100,000 health leaders, and they are exerting their effort to convince others to receive health screening or health checkup. This, I think, would have the more effect than you expect. So it is important to develop the human network within the community so that people would be impacted. So here we have the governors, and we ask the governors to talk to the medical association, and we have as many as 7,000 people in the Aomori Medical Association. I think things would be much better. This is not only about the health promotion, but also about the money making deriving from the health promotion. Then in 2013, we started a Center of Innovation. This is a major project by the Ministry of Education and Technology, and this is one of the largest projects in the history of Hirosaki City. So this is to utilize the companies to do many things. This is something I really wanted to do. So in the past, I said that the health promotion does not make any sense in terms of business. But as I start working there, I realized that if there is no smell or no hint of the money, people would not come to us. So I decided to change my attitude, and as many as 50 the companies are participating since they are smelling money. And then about 20 companies are now giving us money, so we are able to utilize external money. Why is it that we are able to have the collaboration among industry, government, academia, and citizens? So the most important for us is the people. So people should be happy, people should be healthy. Without that, it is impossible to do anything. So that should be the first priority. So we had we were awarded the first prize of the Prime Minister's Award, and the Hirosaki University was awarded for having many health-promoting activities. The most important here is the data. We have data in the center of the structure.
18 years ago, Iwaki Health Promotion Project was started. You do it over 10 days, so you take about 5 hours and test 3,000 items. Not so many in the early days because we didn't have so much money. It takes 100,000 yen per person. So to look at the biome in the mouth or the gut. But we now have more fund with the adoption of COI. So we decided to expand this. And so many people came together, and it's become a huge event. So 100 person per day, 350 doctors and testers, and 100 people coming from companies from Tokyo, mainly manufacturers, because it depends on how you count, but 3,000 items are tested. And you see at the top of the triangle, genomic and the molecular biological data, and then regular data. At the bottom is sociological data. So you have all this data for one individual. And then solution can be searched for each individual. And so we call it the IPS cell data without permission from Dr. Yamanaka. Because you can partner with anyone. I would invite ITER to come to partner with us as well. So people in humanities can participate, of course, scientific people, various disciplines coming together. So how do we collect data? So the yellow part is the 3,000 item health check. So we made that public, very rare for university, and this triggered this explosive growth in the effort. So each of the labs, each of the laboratories, Riken and Institute of Health and Nutrition, they come together. They want data. Of course, we can't give them data for free. They have to participate. They have to come and see. They have to come in contact with the citizens, and they must make their measurements. And then they match that with the 2,000, 3,000 items. And for companies, we charge a fee. It's too precious to provide for free. Non-businesses we provide for free. So we have this unique data in Circle, and that forms part of the big data. So it's growing and becoming larger. So this is for companies. So there's big data in the middle, like Suntory. They want to do research about water. So water is interesting, so they want to do some research about that. Crashier and Lion about dentistry, Eisai, dementia. So they take the data and they use the data. And someone said, your data represents the prefecture with the shortest lifespan, and so it may not be so instructive to lengthen the lifespan, and that upset us. But we collaborate with all kinds of institutions. We want to make it nationwide big data. We're now in a big data era, and we're still falling behind. We can't introduce the My Number scheme. But in 30, 40 years' time, we will be living with all this data. So we should achieve that earlier and accumulate experience. That's what I think we should do. So QOL health checkup is part of that data taking. It's interesting. So come to Aomori and experience it. So metabolic syndrome, this is internal medicine testing, and then there's oral health. If there's periodontal disease, it could lead to a stroke or dementia. Maybe that kind of bacteria impacts the body, and also locomotive syndrome. People say being bedridden is more scary than cancer. So why do we just focus on internal medicine? The health checkup should look at the bone strength, etc. And then there is the psychiatric level. And so you do this for a few hours, and then you get the results. So looking at the abdominal fat with electric current, upper left, lower left, looking at the carotenoid, keratin, and the antioxidants you can measure in about 30 seconds. And we do this in the Iwaki project. And then you gargle. After 10 seconds, you test how what is in your mouth. And then there is the body composition using electrical current. You look at fat and muscle of various body parts. Stand-up test on the right, and then two-step test. So you do it for about 1 hour. After 1 hour, all the data is given to that person who received the test, and they can look at the data and learn about health. I mean, we teach them about health. So it's a fun checkup because you can get the results immediately, and it's a comprehensive checkup. And the various companies are now participating. They want to use a new device, or they want to look at the body form 3D, because people want to become beautiful, and there are various watch devices, and they want to incorporate that. So together with JICA, we went to Haiphong, sitting next to Hanoi, and very popular there. So a lot of data, well, talked about Iwaki data. We have the dementia checkup data, QOL checkup data. So we collect all kinds of data, not just health related, but life log as well. All of that will be collected. And so 3 years ago, a new law for next generation medical information was passed. So all the data from the receipt and personal records are going to be collected from hospitals. It's going to be an opt-out system. So we get the agreement and get the data. Hirosaki City raised their hand first time in Japan, and so that data is also coming in. If it's just Iwaki data, then smoking leading to lung cancer, that may be elucidated. But we want the longer-term data. How does that connect to medical fees, to QOL? We want to learn those things. And if you have a lot of data, then you can do big data analysis, infinite number of combinations. That's what we're aiming for. So I talk about the possibilities of big data. So you could have wide variety of combinations, maybe relationship between intestinal bacteria and oral bacteria, which you never would have thought about. And then second, we can have wide analysis connecting economy, QOL, and purpose of life. And third, you can bring together diverse human resources. So with a cohort survey, it's just by limited number of researchers in a very small scale. It's no longer that is effective. You have to have huge amount of data of certain reliability. And if people can join, even if they're not researchers, then we can discuss with all. And there could be, we can discuss research justice as well. So those possibilities we can't even think about, that can be generated from big data. And last slide, how we intend to move forward. You see RWD, real world data. So this is a data platform. If you just want to collect the data, it's not so easy. You have to have the support from society. And so we make a great effort there. So social capital, human platform, both are necessary. And then you go to the upper part. So you connect big data and individual data. You interact between the two. And you have you create a lifelong personal health record to try to make people healthy. And that will impact all 17 SDGs goals, because it's IPS data. A lot of people can come and join, and it will branch out into new directions. I think that age is going to come. That's what we predict would happen. And Japan will have to shift its course sometime in the future. And Japanese data should not be dominated by GAFA. That will be troublesome. So where is that data going to reside? Well, it doesn't, some may say it doesn't exist in Japan, but some might point out that in Hirosaki there is real-world data, maybe small in scale. Then let's support Hirosaki, is what people might say. That's what I always tell in my talks at the Hirosaki University. Thank you very much.
Thank you indeed, Nakaji-san. The last program is going to be on technical reports. Early realization of the fusion energy will not be possible without the broad participation from industries. Today, we would like to invite 6 companies who are contributing to the ITER project and the promotion of the broadened approach activities to give us a chance to realize that new technologies from Japanese industry are making a great contribution to the development of JT60SA, ITER, and demo fusion reactors. For information, each presentation is going to be in 10 minutes. First, we would like to introduce Allied Material, LMT Coop, Mr. Tomohiro Takita, General Manager, New Market Development Department, and Thermal Management Division, LMT Corporation. This is Takita from LMT Coop. Thank you indeed for this opportunity. I'm really grateful for this. I'd like to introduce some of the challenges for the fusion energy at LMT. This is a corporate profile of my company. Our company deals in tungsten, molybdenum, and diamonds as key materials and was established back in 1939. So we have history of 83 years, and we have a total of 2,000 employees in our group companies. We are a member of the Sumitomo Electric Industries Group. We belong to the industrial materials, one of the 5 business segments, and is engaged in the manufacturing and the sales of tungsten, molybdenum products, heat treatment products, and other products in Toyama, Sakata, Harima, and Awaji. To be exact, actually, we are working on 3 business. In the power and oil business, we manufacture tungsten and tungsten carbon carbide powders and cemented carbide products, as well as recycling products. In the diamond products business, we manufacture diamond grinding and cutting tools and dies. And thermal management business I belong to are involved in manufacturing and selling tungsten and tungsten carbide powders and the cemented carbide products, as well as recycled the products. This shows the initiatives for our growth fields. We have to address mutual relations of the semiconductors and electronic components and 5G components and EVs in automobiles and high-definition medical devices and decarbonizations of energy, and we engage in these activities. It may be rather difficult for you to imagine, but actually we are quite active. We're quite active in the areas where we are not that visible to your eyes. So that said, I would like to go through some of the important activities within my company. The left shows the concept of ITER. The fusion diverter that we are challenging is located under the plasma and neutralizes and discharges the particles that float along the magnetic field lines from the plasma and protects the vacuum vessel from the high heat load from the plasma. It is an important component in the interdisciplinary strategy that determines the power generation capability of a fusion reactor. The tungsten monoblocks introduced here are used in this part. The inner target, for which Europe is responsible, uses about 130,000 units, and the outer target, for which Japan is responsible, uses about 200,000 units, as shown in the red color. Now, the environment in which the diverter is used, the heat load from the plasma and the tungsten content are the same as those in the plasma. The surface of the tungsten monoblock is going to reach a temperature of about 2,000 degrees Celsius. So it's very important for us to look into this very heat, very severe environment, how we can protect ourselves from such an environment. Tungsten actually on the Earth is said to be the strongest vis-a-vis the heat, and I think it has lots of properties actually which is going to be required by the ITER project. Again, it is an issue. Again, it may easily cracked. So I like to again go into details and from these perspectives. We are the only company in Japan that engages in integrated production from raw materials to finished products. Taking advantage of our strength and accumulated technologies, we have developed a tungsten material that is coarse and easily cracked under thermal load, but is not cracked even when exposed to the high temperatures. This is what we have developed. This shows the result of the demonstration test and then high heat load test conducted by the ITER organization. That is shown on the left-hand side. So we are able to prove this in the very first successful operation in the entire world. The right shows the small scale on a testing environment. Again, on the regular tungstens tend to be cracked, but that is not the case when it comes to our the products. So now we truly succeed in developing a tungsten that is resistant to the thermal shock. This shows the status of our company's efforts toward the nuclear fusion. JT60 back in 1950, and again we have been successful in developing the heat-resistant materials. Actually, 120,000 DACs and actually units and actually to be utilized in the ITER. So we are able to visit an ITER. In that year, actually, since then, actually, we are making our best efforts for the mass production. So, in terms of the mass production, I've just talked about the quality of the tungsten materials. Actually, Toyama City and Toyama Prefecture actually raw materials and producing all the products, and also we have Yamagata and Sakata City actually to have the further activities. At the Sakata City actually in October last year, we launched a new production line. And as of now, the outer target actually 370 types, actually 120,000 units being challenged. In terms of quality control, actually monoblocks and 2D touched, so we can actually have the traceability unit by unit. And also we are having the required activities in an automated manner. Out of these efforts, and actually we're improving our quality. Furthermore, actually the projects for European side actually started back in 2018. Actually, we became a kind of the contact point, and actually with the target manufacturers, and we are happy given this an opportunity. Actually, in order target for Europe and tungsten monoblock. Actually, our products versus our products and only the Chinese products are going to be allowed. In October this year, actually, one half have been already delivered, and we are making further adjustment in terms of delivery. And then OBT experiences and high quality we have accumulated in Japan should be applicable to the efforts in Europe. That's what we would like to do. Okay, beyond an ITER, here I'd like to look into the competition aspects. Actually, we need to now, of course, develop new materials and new technologies, and QST and then other the organizations and are actually united with us to have further collaboration. Actually, we are having the monopoly market and in the fusion area, resulted in quite an active venture activities. Yes, and we are feeling this very keenly. And the human resources are going to be quite important, and also we need to further develop sophisticated technologies. So we'd like to make further contributions to realizing the fusion energy based upon these aspects. Again, we have a tungsten monoblock, which is supposed to be really good in terms of quality, and also we have the well-established heat-thinking products as technology. And going forward, definitely this thermal issue is going to become a lot more serious and critical. And actually, we happen to have the strength in the heat sink products. We have lots of experiences in this area. So we should be able to make our contributions in terms of management and heat. And also, of course, we need to have money. So it is going to be quite important for us to have good collaboration together with the government and also in academia. And out of this trilateral collaboration, I would like to make further contributions in further improving our technology and our expertise. Lastly, we need to actually address global warming issue, and this could be solved by the fusion. And actually, our keyword, carbon neutrality, is here. So now we have to make further efforts and to reach the safe and secure energy. This concludes my presentation. Thank you indeed.
Thank you very much, Mr. Wakida. Next, we'd like to invite Canon electron tube devices. We would like to ask Keiichi Saito, the leader of the development, to take the floor. Mr. Saito, the floor is yours. Thank you for your introduction. I am from Canon Electron Tubes and Devices. My name is Saito. Thank you for this opportunity. Today, I will speak about the efforts to develop electron devices for nuclear fusion and accelerators. This is the structure of the presentation. I will introduce the overview of the company. I will then speak about our efforts for nuclear fusion and the efforts for accelerator. And then after that, I will speak about the actual introduction and then of the products and the application of technology, which will be followed by the summary. We have been contributing to the society by developing and manufacturing the key components for medical inspection science research field. So we have X-ray tube, which is here we have the X-ray tubes and then the microwave tubes. This is again the wave emitting tube. And so these are the keys. And this is the history of the company. In 1915, in the midst of the First World War, X-ray for the medical, the application was not available. So we decided to create the X-ray tube in Japan. And then we shifted from Toshiba to Canon. And then the new company was created, which is the Canon Electron Tubes and Devices company. And then we have 350 of the race stations. So we have there are as many as 350 the race station of the heritage for the future technology, and 5 out of 250 was ours. And then we have the gyrotron. I will speak gyrotron development in 1979. I will speak about that later on. And here I will speak about our efforts for nuclear fusion. In order to cause nuclear fusion, the plasma must be heated to several hundred million degrees Celsius, which is done from the outside. And one of the most effective heating methods is to inject microwaves into the plasma. And then in the case of the electric oven, it is 150 watts. But in the case of gyrotron, it is 100 million watts. So it is 2,000 times that of the oven, electronic oven. So here there are 8 gyrotrons being procured in the ITER, and we are responsible for 8 of the 24 gyrotrons. And here, please take a look at the left-hand side at top. And as I just said, the temperature level is 1 million degrees. So here we are using the term the window of the output because of the high temperature. Sometimes it breaks. And then we are utilizing the enhancement of cooling using the diamond window with the TSC. And so we introduced that. And then on the left-hand side, bottom, optimization of inner surface shape of radiating part. So we conducted the simulations, and based on the simulation, we decided to come up with this design. On the right-hand side top, we talked about the G3, and this is the energy recovery technology. With this, it is possible to enhance the conversion, and also we are able to reduce the gyrotron size. And this has been repeatedly mentioned. We created 8 gyrotrons out of 24. So that was a collaborative effort with QST, and we passed the acceptance test. And also, this is a press release by QST, and it says that we were able to create all 8 of them. And this is similar to this. This is a klystron, and this has been utilized in various fields of technology and science. One is the RIKEN in Harima, and they are being used for the X-ray, the free electron laser. And the Sakura, our klystron, had been introduced in 2013, and it was awarded the Minister of the Next Award. And the Skytree was awarded the Prime Minister's Award. So we were not in line with the Skytree, but still we were happy. And then Dr. Koyashi and Dr. Masukawa, they used the high energy accelerator in order to confirm their theories. So this has been contributing to the advancement and progress of science and technology. We have many such facilities in many parts of the world, US, in Europe and Asia, and the electron tubes are being used in many places. This is CERN in Europe, and this is ESS in Sweden. So they are being used in many places like this, so that it can make a major contribution to the advancement of science. So, and then, as we said, we have the simulation technologies which have been developed and also utilized in the ITER project. On the left-hand side, we have the 2D project, 2D simulation. In the center, we have the red line. And so this is a very rough 2D simulation that we used for the development of the design. But now we have 3D simulation. Dynamic, the electron situation and the amplification status is confirmed utilizing this 3D system, which is conducive to a very efficient development on our side. And then all these are now used in the different application fields. One such example is medical industry. This is a LINAC for the cancer treatment. And also, as was mentioned, this is a boron, the neutron, the catching technology, or this is BNCT. And this is a summary. We are making contribution for securing independent energy resource. We don't have to worry about depending on the rest of the world. So secure and safe energy sources are important. And then in order to do that, the gyrotron, we have to fulfill our responsibility as a manufacturer of gyrotron. First is the creation of product with a much lower the environmental load, and also the highest efficiency and energy collection technologies in compact size, and also ITER project. Therefore, we have already submitted 8 gyrotrons for ITER, and then we deal with the needs for the further enhancement and the maintenance, and also demo. We will see the increased number of demo. So we have to work on the commercialization project, and so the completion level and also the performance level should be enhanced. Last part is, I think this is the most important. With human resources development, it is important to hand down the technologies and the skills of the human resources. So I think we have to continue working on this, and alongside with your support, we would like to continue doing this. And we are in the manufacturing business, so materials are very important, and the collaboration with suppliers is the indispensable. So we'd like to grow with the support of the suppliers. Thank you very much. That's all.
Thank you, Mr. Saito. Next, from Teikoku Ion, we have President Mr. Nakamura Takashi. Mr. Nakamura, please. I'd like to report on the development of uniform thin film plating technology for inflexible cables using mineral insulation materials. This is Nakamura of Teikoku Ion. First, here are the members who collaborated to develop this. So, Okazaki Manufacturing provided test materials and conducted a quality evaluation. Teikoku Ion devised a plating method and implemented the plating. And then we received the final confirmation. And also project coordination was done by the QST, National Institute for Quantum and Radiological Science and Technology. So these three parties collaborated in this project. So Okazaki Manufacturing Company, a brief introduction. It's located in Kobe City, established in 1954, has 13 domestic sales offices and 6 domestic manufacturing plants, 3 overseas affiliates. Number of group employees is 800. Products include thermocouples, resistors, and MI cables, and also industrial heaters. So they manufacture and market those products. Next, I introduce Teikoku Ion. Head office and plant are located in Higashi Osaka City, famous for being a small business town. Surface treatment company mainly engaged in hard chrome plating and electroless nickel plating for functional plating. It's able to offer ion hard plating, a plating film with very high corrosion resistance, and ion diamond plating, a plating film with low coefficient of friction. So they have these unique technologies. So now let me explain about the plating challenge that we have taken on in terms of the MI cable plating. So Japan is responsible for the development of the MFC neutron measurement system using a small fission counter called a microfission chamber, which will be installed inside the vacuum vessel. So the MFC detectors will be mounted on the upper and the lower sides of a bracket module inside the vacuum vessel. Inorganic insulated metal MI cables are used to connect the detectors. So the target was to satisfy this very stringent quality requirements of ITER. So it's very high temperature and high radiation inside the ITER. So using this MI cable, well, we conducted a verification for its use. But then there was a problem. So high temperature plasma is maintained in ITER by injecting microwaves. Part of the microwave heats and damages the MI cable, and that is a problem. So to prevent the absorption of microwaves, copper plating is effective, but if the plating becomes too thick, then there will be electromagnetic impact. And so as a countermeasure, 5-micron copper plating is proposed to the entire length of the MI cable surface to reduce microwave heating. And the increase in the electromagnetic force is limited to 20%. So ITER's requirement was plating of copper with a uniformity of 5 plus minus 1 microns over the entire length of the MI cable, and plating of more than 100 microns at specified portions of the MI cable. But using conventional plating methods, reel-to-reel or batch method, did not satisfy the requirements. You could not plate the MI cables with those existing technologies. So the three parties worked together and developed a new technology, a rotating plating machine for the MI cables. This is the schematic. The MI cable is wound in a spiral shape, and the MI cable is rotated. The jig is rotated. The key point is to vary the rotation speed and the central axis. By moving the anode as well, the difference in distance between the electrodes is eliminated. The plating deposition rate greatly affects the film thickness, so we eliminate bias between electrodes. By varying the center of rotation, anode position, and rotation speed, we realize uniform plating thickness over the entire length of the MI cable surface. The uniformity of the contact points that energize the MI cable is achieved by the outer circumference of the fixture and a mechanism that allows movement of the contact point on the outer circumference of the jig. The contact point between the cathode and the cable is point contact. The contact point was successfully optimized and the area is minimized. Thick plating of 100 micron or more at specified points was achieved with the use of plating mask jig and by optimizing conductivity. So this is measurement after the plating. 5 micron plus minus 0.5 micron is achieved, satisfying the requirement of the ITER. So it's a high accuracy and high quality plating technology. And the three parties obtained a patent for this plating method and the device. And we're applying for patents overseas as well. So this shows the plating process. So as you see, the plating jig is rotated. By shifting the central axis slightly, you do the plating. This is after the plating is completed. So MI cable is wound in a spiral, and you see very clean copper plating. The most difficult requirement of ITER is to plate in this limited area, but the blue part is where 5 to 100 is where it shifts from 5 micron to 100 micron plating thickness. You can see it's tapered, and you have the clean finish. So to summarize, we have developed a new rotary plating machine which has realized the high precision plating that meets ITER's requirements. We obtained a patent for this, and in March of this year, plating of 8 MI cables and 4 exhaust pipes for ITER were completed. In July, we received an acceptance from the ITER organization as the first Japanese instrumentation equipment. The plating technology developed this time enables plating of hard and long wires in a uniform way, which was not possible with conventional methods. And also we developed a technology that applies thick partial plating only on designated areas. And using this technology, we have copper on MI cables, and so the three parties jointly made a press announcement, and it was featured in newspaper articles as shown in the slide. Lastly, We are very appreciative for having the opportunity to develop copper plating technology for MI cables. Thank you for your attention.
Thank you indeed, Nakamura-san. Next, from Toyo Tanso, we are going to have Mr. Masatoshi Yamajin as the presenter. He belongs to the Atomic Energy Section Production Division. First of all, I'd like to actually express my sincere appreciations for the opportunity given to me. Thank you indeed. Thus, actually, I work for a company called Toyo Tanso. My name is Yamaji. The name of the company, Toyo Tanso, probably not many people are familiar with this company. For the past several years, actually, even at my family, actually, the carbons, tanso in Japanese, actually, my family members actually referring to the tanso and carbon. Again, COP21, decarbonization, zero carbon. And within my family, and actually, your company is okay, dear father. Again, I just wanted to introduce some of the dialogues we're having. Again, centered around the carbon. Actually, with this morning in mind, I have produced a set of materials for my presentation. The first, the history of the Toyo Tanso Company Limited, and also what is the carbon tanso. Again, I'm sure that you are familiar with the word, but probably you are not familiar with the details behind the carbon and the main applications, overall applications. Also, I'll go through the graphite manufacturing method. And also, we are also involved in the special materials. So now I'll cover these points. Toyo Tanso actually was created back in 1947. And in 1974, actually, we actually succeeded in the mass production for the large in size isotropic. And actually, the founder is originally from the Kagawa Prefecture in Shikoku. So all the facilities actually are located in Kagawa Prefecture. Actually, I traveled up to Tokyo from Kagawa Prefecture today. Actually, we are listed in the first section of Tokyo Stock Exchange in 2006. This shows the major outlines in our factory and operations, what we do make. We have those the carbide and block, quite large in size, in a nutshell. Then, of course, then we move on to the products, and then products are going to be delivered to customers, actually producing them in Japan, and also we are selling those products and outside Japan as well. What is carbon now? Well, you are the experts. Well, I'm sure that you have learned about this theme. What is carbon during the junior, senior high school days? But again, if now I go through the highlights, the element, the symbol is C, and also the carbon, the number is 6, and also the atomic weight is 12.0111. So diamonds and fluorine and carbon and carbide actually are some of the materials, and actually people are studying. Actually, what is graphite? Actually, 2,500 degrees and higher. And actually, graphite can be actually used in such a severe condition. And also good thermal conductivity, and also good and heat resistance, and also the chemical resistance is really good. Next, I'd like to go through the main applications. This shows the typical applications and for your better understanding. Several areas, and actually graphites as materials. Actually, I used in rather the invisible in areas. I think some examples are shown here. In the advanced technology, for example, Hayabusa ion engine. Several years ago, and of course, there was I don't know how to put it. And actually, there was challenges. Actually, they are not able to come back to the Earth. So the Britain of engine actually has used our materials, and also in the transportation field, pantograph of the trend systems actually does use our materials, and also the actual silicon monosilicon circuit heater and others, and also for the general industrial applications. For dyes and for the continuous and casting and others. Again, in terms of nuclear power and application, actually in the fusion of the reactors and HTGL, and today now I'd like to actually go through details behind this fusion reactor. The left shows on JT60, and the right shows inside the reactor actually HTGL. High temperature and GL. Actually, this is located at the Japan Nuclear Research Institute. So they are using our the products. Next, I'd like to go through the characteristics of the materials. We have the CC composite and also the graphite. CC composite has the following attributes. Actually, high thermal conductivity, higher than copper. So this is one of the salient features. This is really good. And also the graphite. Compared with the CC composite, actually, thermal conductivity is way too low. But again, this is one possible application area. Actually, inside the furnace, actually, they are used on the wall. Next, I'd like to briefly explain the manufacturing process of CC composites. This is something quite special. Actually, the graphite and felt, and also what we call the matrix, actually, the thermal setting resin being utilized. And it has following features. Actually, higher conductivity, thermal conductivity is quite high. Because of this, and actually, again, this material is in great demand. If it is composite materials and actually graph materials, actually the strength is going to be quite high, but this material has the rather weak the strength, and this makes it rather unique. Next, I'd like to go through the manufacturing process of the carbon materials, and actually the isotropic graphite the processing, and the coke and the cold hurl pitch and then others are being utilized, and also the production is going to be quite unique. I'll come back to this issue later. So actually the temperature is going to be 1,000 degrees, and actually for sintering, actually ultimate temperature here is going to be as high as 3,000 degrees. So this is going to be a basic process and to manufacture the graphites. And it all depends upon the customer specification, and we are quite flexible to meet with customer specification. This shows the basic molding method. The left shows the cold isostatic press method, CIP. So then tile materials for the nuclear reactors, and also we have the extrusion and also die mold and die molding, XYZ. The three directions, and actually the attributes are going to be exactly the same in the three directions. So this is why this is in great demand. Next, I'd like to go through some of our track records, so to speak. QST, JT60 and SA. Actually, we're able to deliver products for this, and actually, and below shows the helical type and LHD furnace. So actually, we're able to actually develop products. Actually, this was back in the 1990s. So we started businesses back in the 1990s, and actually, we have a long history with these materials. Finally, I'd like to go through the special materials and development products. What you see here is our materials, by the way, actually are not used on the ITER side. ITER actually, the beam actually to measure the ITER beam, actually, for that purpose, our materials are used. Actually, this has very special the attributes, and actually, the thermal the conductivity is high only in one direction. CC composite only one direction. Thermal the conductivity is going to be quite high, 650. Quite high, 650 volt, and we have the device called the spider. Actually, this is the unit to make a measurement. Actually, this is the name of this is called the strike. Next, I'd like to move on to the diverter side. The CC composite by us and actually is not used for diverters. Well, someday in the future, we are hoping that you will use our diverters. So, with this point in mind, we have developed these characteristics. We have a tungsten to be connected on the CC top. So, we are developing this right now. I think it will take some time before you can actually use this. Yes, I know this for sure, but someday in the future, 5 years from now or 10 years from now. So we are making our slow but steady efforts in our R&D phase actually to develop the special materials to benefit you. Now the summary. Actually, isotropic carbide and also CC composites by us, Toyo Tanson, actually, they are continuous to be used on the reactor the surface. Of course, there are issues and problems. Actually, we need to actually develop new materials in order to address these issues and challenges. Thank you indeed for your kind attention. This concludes my presentation.
Thank you very much, Mr. Yamaji. Next, we'd like to invite the representative from Microwave Chemical. The speaker is Mr. Tsukahara, Director and CSO of the company. Thank you for your introduction. My name is Tsukahara. I'm from Microwave Chemical. First, allow me to take some time to explain to you the connection between microwave chemicals and the fusion technology. We produce beryllium and the lithium, and we scale up the production to make it commercialized. And at the same time, we are working on the microwave process. So we are trying to change the picture of the society with electrification. And in the case of the nuclear fusion, the nuclear fusion generation would give us a major opportunity to come up with the power generation the method without the emission of the carbon. So today I'd like to speak about what we do with the TST, which is the dissolution of beryllium and lithium from the ore. And also I will speak about our scale-up technologies. First is the beryllium dissolution, the demonstration with QST. This is the first report that we are making in front of the public. The QST had the SEES technology, and we have the scale-up technologies, and so this is the outcome of the combination of the two. Up until just recently, beryllium had been extracted with 2,000 degrees centigrade, so the situation here is very hard. And so QST allowed us to use the dissolution processing using the microwave heating, so we were able to reduce the temperature to 300 degrees, and we are now in the demonstration. The equipment has been sent to QST Aomori, Kasho, and the demonstration was made. And then this is the outcome here, and as can be seen, this dissolution rate was 100%. So this way, we were convinced that we are able to scale up this process. So the temperature was down from 2,000 to 300. So this is energy conservation technology, and also it is, needless to say, conducive to the reduction of the CO2 emission. This is another thing that we have been collaborating with QST. So this is the lithium dissolution or the dissolution demonstration from spodumene, and this is the report made in this year, January and July. So here we used the dissolution. We had the dissolution demonstration using actual ore, which is spodumene, and we were able to have the major cost reduction for capex, opex, and CO2 emission. So this is a major performance gain for that new process. This is a roadmap. For lithium and the beryllium, we have different roadmaps for that. So first is the lab development, and the QST had been working on it. And for the small size demonstration, we participate. And then this year in 2022, we were able to complete this process for lithium. And for 2024, we will have 500 tons to 1,000 tons of large-scale demonstration. In 28, we will have a demonstration for, well, actually, this is not the demonstration, but rather implementation of 20,000 to 30,000 tons. In order to make the time for to be ready for the nuclear fusion, we are planning to have 100 tons to 200 tons of demonstration, and the implementation time frame should be 2040. This is a QST team. We are collaborating with them. Mr. Nakamichi is a leader. We have Dr. Nakano, Dr. Akamizu, and Dr. Yokohama. These are the wonderful individuals as a team. We have been collaborating with them, and we are committed to continue working with them. And this is a corporate overview. So I'd like to speak about the scale-up technologies of the company. This company was established in 2007, and we decided to have a research using the microwave chemistry technology platform, providing solutions from development to engineering. This is microwave. This is not about heating, but rather this is the energy transmission method. So the microwaves are a type of electromagnetic wave and are used to cellular phones and others. And so this is the ordinary process, the conventional process. This is the heating from outside, but this one here is from inside. Why is it that it is possible? Because of the fact that the frequencies of to absorb microwave is different, so we have the different the wavelengths being absorbed. So we do not insert energy inside the solution. So we have the enzyme and also the substrate, and energy is directly inserted here. And this way, we are able to increase the processes efficiencies. And in 1980s, they started using microwaves in the chemical industry, but scale up was very difficult. So it was impossible to move on to the commercialization. We are one of the companies to work on this, and we were successfully able to work on this. And also we are able to work on the other areas as well. So what kind of benefits are we able to expect? There are three things, I guess. One is the manufacturing process improvement, and also this will lead to the energy conservation and development of new materials, and thirdly, decarbonization, which is the reduction of CO2. So these are the three major areas or benefits of this innovation. This is the actual case. So we have plants to whom we submitted the products, and so here we have organic, the synthesis, and also the dissolution and the others. So you are able to see the level of reduction with our technology. And let me explain to you how we were able to come up with this process. We have started with the technology platform. Many of them are the problems of the society, problems of the customers, and then we have the database. We have the database of about 5,000 databases, and then we are able to look into the areas of the similarities, and then on the right-hand side we evaluate the basic properties, and then this way we are able to come up with the designs, and then we are able to work on the design of the substrate for the reactions, and then we have to work on the understanding of designs of the microwave, epsilon double prime, and E. These are the two keywords. So let me explain to you what they are. Epsilon double prime design is shown here. To what the design, the energy is transmitted. So first is the reaction system, and then with this, in order to embody that, we have to work on the reactor design. So when we say reactor design, it is important to understand how we are able to transmit and distribute microwaves. Especially important is the limit. Now, the first is about the reaction system design. I'd like to be brief here. This is a quite simple matter. So the most important is what absorbs microwaves to what extent and under what conditions. This is what we have to understand. The energy would be transmitted to the materials, and then, generally speaking, this will be put into the form of the heat, and then we have this is the water and alcohol, and then submarine. This is the loss of this, and then on the right hand side, the iron and the cobalt, and so epsilon double prime. This is about the dielectric. So here we have the magnetic body and magnetic field. Everything would become more and more complicated. About the epsilon double prime, a microwave would be absorbed here, but it is dependent on the heat and also the frequency. In what way are we able to select it, control it? So which frequency to choose is important. And then the next is the reaction. So reactor should be designed properly, and so the absorbance is the entered, and then we have the connection of the electromagnetic field analysis and also other analysis of MW. And then this is the patent strategy. Basically, we obtain the patent not only in Japan but also in the rest of the world. We have to look at history. We are not able to change the society overnight, so we have been doing many things for many years. So these are the kind of things we have done in the past. And finally, I'd like to speak about carbon neutrality. Our microwave process is a better process, so it has a major contribution for the reduction of CO2 emission. The logic here is not about LNG, not like LNG. So the ITER and also the nuclear fusion energy can be used. And so this way we are able to reduce the CO2 emission. That's how we are looking at it. It's totally different from a fossil fuel. And then this way we are able to change the energy into the heat. So this is totally different from IH, and scale up is much easier. We are in the field of petrochemicals and also the ore mining processes. So I think we are able to utilize this technology here. Crackers and chemical recycling and hydrogen. Then here, this is for the mining industry, the lithium, beryllium, the extractions, and other technologies are used, and also the firing process or the firing processes are also able to benefit our technology. Thank you very much. That's all.
Thank you, Mr. Tsukahara. Next, from Universal Materials Incubator, we have Associate Mr. Hirai Yuji. Mr. Hirai, please. Thank you for the introduction. I'm with Universal Materials Incubators, UMI. I'm Hirai. So this is a little different. We worked on this commercialization aspect, so let me share what we've done. So it says commercialization of innovative lithium production technology. So we worked with QST as business promoter. So first, briefly introduce UMI. UMI became independent from INCJ, carved out in 2015. We are a venture capital, but we focus on chemicals and materials companies, and we are globally famous as a venture capital in that field, and we have such unique characteristics. So why do we focus on materials and chemicals? That's because they account for 30% of Japanese GDP, and at the scale-up stage, large amount of funds and long time is necessary, and there is a need for big support at that stage. So our concept is that at the scale-up stage, we assist the companies to achieve their targets, and we make investments to support them. As a venture capital, we make investments, but not only that, but in terms of business creation, we are active. So technology from academia, we commercialize through incubation, and we source technology from large companies, and we invest in venture companies, and so we connect the ventures with large companies. So new business is generated in the chemicals and materials industry. So we have a vision of creating this kind of circular cycle, and UMI wants to continue to act as a hub for these various parties. We're very fortunate that large chemicals companies have been joining us as LPs. So as part of incubation activities, under the JST START program, we use subsidies and also QST technology to work on commercialization. The background is that well, we focused on the lithium market. As you know, EVs have become quite popular. Technology has been developed and it has been socially implemented. That requires huge amount of lithium, high quality lithium. Demand is increasing, and that's become an issue, and there is an outlook that there will be a gap between supply and demand. There's a strong need for this gap to be filled. In terms of market price, compared with 2-3 years ago, 5-10 times price hike or price rise is expected, and price rise is expected to continue. And the reason is due to the manufacturing method of lithium. There are two major methods. One is brine method, so you start from the salt lake. Then there is the mining method, so you mine from a mine. And the brine method, making from salt lake, it's low cost, that's a benefit, but you have evaporation. Using solar heat, it takes more than 1 year, so it cannot meet short-term demand. The mining method, you need a lot of energy and reagents, so it can become costly, and also it emits large amount of CO2. So those are the issues with the mining method. Looking at the current production volume, left-hand side, you see the pie chart. So about half is from the mining method in Australia. And the reason is they can provide short-term supply. And then, well, if you look at the amount of reserves, the brine, salt lake water in Chile accounts for more than half. So high efficiency production in the salt lakes and large volume production in those salt lakes would be desirable. So we took the technology by Mr. Hoshino of QST. It's an innovative technology. And we felt that we can solve the lithium supply issue, and we worked on commercialization. The unique characteristics of this technology is that you can have an ionic conductor. in liquid, and it's fast and it's high purity. On both sides of the ion conductor, you would have ion charge, and the lithium can move continuously, and there's high selectivity, so you can have 99.99% purity. And so in the brine, you can eliminate the long lead time, and you can have the high quality lithium that is required for EVs. So this can provide a solution for those needs, and it's a groundbreaking technology in that regard. And so small stack equipment was used to verify the continuous operation. And after this startup will be established, bench scale demonstration should be conducted. So as a startup, as the business model should be a license model. And the unique characteristic of this is that you have an ion conductor, and so you can sell that as consumables, and so you can have recurring income. So the expected customers would be lithium manufacturers or lithium-ion battery recycling companies. So a clear benefit can be provided to those customers. In terms of partnering, we think that is important, especially for technology development. The ceramic film manufacturers and equipment manufacturers, we have to work with them. After the device is developed, you have to provide a demonstration to customers. So we have to partner with various manufacturers. So using UMI network, we are working to forge those relationships. Currently, we are planning scale up. Well, after startup is established, this is the schedule that we have. Major benchmarks in 2025 POC for sure, and before that, technology development should be made, increasing the performance of ion permeation and accumulating know-how manufacturing. And by achieving POC, we will be able to have the funding of the startup, and we can have it adopted by the lithium manufacturers. And finally, the new startup to be established from a resource perspective can have a big impact to Japan and the world. So using PV and other renewable energy, it could be green materials. And for lithium-ion battery recycling, you can recycle precious resources. And in the future, you can extract lithium from seawater. And there's potential for separation of 6 lithium. And that could provide raw material supply to nuclear fusion and can have big impact there as well. So from resource perspective, the startup to be established will have the capability to show big impact in Japan and abroad, and we are supporting with big expectations. That's all from myself. Thank you.
Thank you indeed, Mr. Hirai. With this, and I would like to close off the technical report sessions. Well, thank you for your participation for a full day. Again, this has been the meeting of the annual symposium for the ITER and the BN activities. On behalf of the organizers, actually, I would like to have Professor Hiroshi Yamada, who serves as the chair for the ITER and BN the annual sessions, as well as for the general meetings and also the organized committee. Without further ado, Professor Yamada, please. Thank you indeed for your kind introduction. This is Hiroshi Yamada. Again, I serve as the chair for the organizing committee for the ITER BN symposium. If I may, I'd like to take a moment to express our heartfelt appreciation going to each one of you. This auditorium also we had in YouTube distribution. I'm so happy we had so many people participating in this meeting. Actually, we have the full capacity and more than 200 people in this auditorium. And unfortunately, we had those people now who could not make it, even though you wish to be here in person. My apologies. Again, this is a meeting looking into the activities and for the ITER and also BN activities, also JS60, and also the feminine epidan, and also the accelerator test. Actually, we were able to observe the good progress, and also we are able to identify some of the issues and challenges we have to address and overcome. So this the progress now we have achieved, of course, and are coming from all the contributions efforts coming from those people who are working really hard in the field. And also, we are so grateful for the presentations, and actually presentations made by the many people from the government side, academic side, and also from the industry side. We are enjoying really good success thanks to the good support coming from the community as well. Again, I think we are aiming at this important the goal for the whole entire human beings. Would like to succeed in this fusion energy creation. I'm sure that in this journey we will bump into lots of issues and difficulties, and we have to be able to overcome those challenges in front of us. We are still in our journey. We have not completed this journey. So it is very important for us to be able to share the important challenges and problems. Actually, this is going to be the nuclear the technology, and actually this the fusion to benefit the entire human beings. We have to be truly united in order to actually deliver such a success and benefit to the entire human beings. Again, on ITER, actually, we are so sad because we have lost the Bernardo Vigo, the former DJ. But actually, we're so happy. New members, including Pietro Barabaschi, for ITER, and also the Professor Nakajima and others. I'm sorry, due to the time factor, we simply cannot make a reference to your names. But actually, QST and actually staff people, and also all the participants, actually, I'd like to express our sincere appreciation going to each one of you. With the COVID-19 actually affecting us, and of course there has been some restrictions, but again we're able to have the business and panel, and also we're able to have the good opportunity and actually to exchange and opinions dialogues among all the people concerned. Again, many people involved in setting up these meetings. I'd like to thank you, and also we're moving toward the end of the year end, and I do hope that you can truly enjoy the good year and actually enjoy the good New Year's. Thank you indeed for your kind time and attention. Thank you. And thank you, Professor Yamada. Well, even I like to offer my sincere apologies, and I'm not good to moderate the meetings like this. But again, I'd like to thank you for your kind patience. Thank you indeed for your support. That's it. This concludes on ITER BA and actually Annual Symposium 2022. If I may, I'd like to ask you